Hello there and welcome to Science for Sleep, where curiosity gets comfortable and big ideas are given plenty of room to stretch out, breathe, and wander gently through the mind. Tonight's slow journey is going to drift into a question that has been quietly reshaping modern physics, a question that starts with something very familiar and ends somewhere rather strange. Scientists are beginning to wonder whether the stage we thought reality was built upon, the combined fabric of space and time, might not be the most basic layer of the universe after all. Before we settle into that thought, let me ask you something simple and personal. Where are you listening from right now? Is it late evening, early morning, or somewhere in between where the light outside hasn't quite decided what it wants to be yet? And if you happen to glance at a clock, what time does it say in your little corner of the world? It feels fitting to check, given that tonight's story is about what time and space themselves might really be made of. If you find this gentle exploration soothing, or if it helps your thoughts slow down after a long day, you're always welcome to leave a like or subscribe to this small, quiet place where science is allowed to move at a human pace. It helps these calm conversations find their way to others who might need a soft landing for their thoughts as well. Now, let's begin, not with something exotic or distant, but with the most ordinary experience you can imagine. You're sitting somewhere. There is a sense of here. There is a sense of now. Your body occupies a position in space, and your awareness drifts through time, moment by moment. These two ideas, space and time, feel so basic, so unavoidable, that it's hard to imagine reality without them. They are the background of every memory, every movement, every plan you've ever made. When you think about yesterday, you picture a different time. When you think about another place, you picture a different space. They seem like the container that holds everything else. For a very long time, physics agreed with this instinct, even when scientists discovered that space and time were not separate, but woven together into a single structure called spacetime. They still treated that structure as fundamental. It was the arena where all particles moved, where all forces played out, where every story of the universe unfolded. In Einstein's theory of general relativity, space-time is not just a passive stage. It can bend, stretch, and curve. Massive objects like stars and planets shape it, and that shaping is what we experience as gravity. In this picture, space-time is dynamic, flexible, and powerful, but it's still the thing that everything else depends on. For much of the 20th century, this view worked astonishingly well. General relativity explained the motion of planets, the bending of light around stars, the expansion of the universe, and the existence of black holes. At the same time, another branch of physics, quantum mechanics, was revealing an entirely different layer of reality, one where particles behave like waves, where uncertainty is built into the rules, and where observation itself seems to play a role in shaping what happens. These two frameworks, relativity and quantum mechanics, are both incredibly successful in their own domains. Relativity handles the large, the massive, the cosmic. Quantum theory handles the small, the light, the subatomic. The trouble begins when you try to make them work together. When you push into situations where gravity is strong and distances are tiny, such as near the centre of a black hole or at the very beginning of the universe, the equations start to clash. The smooth, continuous space-time of relativity does not sit comfortably with the jittery, probabilistic world of quantum mechanics. This tension has been sitting at the heart of theoretical physics for decades. It's the reason scientists talk about the search for a theory of quantum gravity, a framework that can describe gravity using the same quantum language that works so well for the other forces of nature. And it's within this search that a surprising idea has slowly taken shape. What if space-time itself is not part of the fundamental machinery of the universe? What if it is something that emerges in the same way that temperature emerges from the motion of molecules, or sound emerges from the vibration of air? To get a feeling for what that means, it helps to think about temperature for a moment. When you touch a warm cup of tea, you experience heat. You can measure it with a thermometer. You can describe it with a number. It feels very real. But at a deeper level, temperature is not a basic property of any single molecule in the tea. An individual molecule doesn't have a temperature. It has a speed, an energy, a direction. Temperature only appears when you look at a huge collection of molecules together and describe their average behaviour. In this sense, temperature is an emergent property. It's a useful, reliable concept that arises from something more fundamental, but it's not written into the deepest layer of physics. Some scientists are now wondering whether space-time might be similar. Perhaps it feels like the basic backdrop of reality, because we are large, complex systems made of countless interacting parts. From our perspective, space and time are the natural way to organise our experiences, but at the smallest scales the universe might not be built from points in space and moments in time at all. One place where this idea starts to show itself is in the study of black holes. These objects are extreme in almost every sense. They are regions where gravity is so strong that not even light can escape. According to general relativity, a black hole has an event horizon, a kind of boundary that marks the point of no return. Once something crosses that boundary, it is cut off from the rest of the universe. In the 1970s, physicists began to realise that black holes are not as simple as they first appeared. They seem to have a temperature. They can emit a faint form of radiation, now called Hawking radiation. And they have an entropy, a measure of how many internal states they can have. This was strange, because entropy is usually associated with microscopic details, with the number of ways a system's components can be arranged. But a black hole, in classical relativity, is supposed to be simple. It's defined only by its mass, its charge, and its spin. The fact that black holes have entropy suggested that there is a lot of hidden information associated with them, even if we can't see it directly. More intriguingly, the amount of entropy a black hole has is not proportional to its volume, as you might expect if it were related to the stuff inside it. Instead, it is proportional to the area of its event horizon. This led to a bold idea known as the holographic principle. The holographic principle suggests that all the information contained in a region of space can be described by data stored on the boundary of that region, much like a three-dimensional image can be encoded on a two-dimensional surface. In some theoretical models, a whole universe with gravity inside it can be equivalent to a quantum system without gravity living on its outer edge. This is more than a clever mathematical trick. It hints that the space inside might not be fundamental at all. The deeper, more basic description lives on the boundary, in terms of quantum interactions that do not obviously involve space in the way we usually think about it. The familiar three-dimensional world we move through could be something like a projection, an effective picture that emerges when many quantum pieces work together in just the right way. Another thread in this story comes from the study of quantum entanglement. Entanglement is a phenomenon where two particles become linked, so that the state of one cannot be fully described without reference to the other, even if they are far apart. Measurements on one instantly affect what you can say about the other, in a way that doesn't fit neatly into the idea of signals travelling through space. In recent years, physicists have started to suspect that entanglement might be deeply connected to the structure of space-time itself. In some theoretical models, the amount and pattern of entanglement between quantum systems determines the geometry of the space that seems to emerge. Regions of space that are close together are those whose underlying quantum degrees of freedom are highly entangled. Areas that are far apart have weaker or fewer connections. From this perspective, space is not a pre-existing grid that particles sit on. Instead, it is more like a map of relationships. Distance becomes a measure of how strongly different parts of a quantum system are linked to each other. Geometry, which we usually think of as something fixed and objective, starts to look like a summary of deeper, more abstract connections. Time, too, begins to look different in this light. In some approaches to quantum gravity, time does not appear as a fundamental variable in the basic equations. When physicists try to write down a quantum description of the entire universe, they often end up with formulas that do not include time at all. This leads to what is sometimes called the problem of time. If the deepest laws of physics do not refer to time, how does the flowing sense of past, present, and future arise? One possible answer is that time, like space, is emergent. It might come from the way complex systems change relative to each other. Instead of a universal clock ticking in the background, there may only be correlations between different parts of the universe. When one system changes in a way that is consistently related to changes in another, we interpret that pattern as the passage of time. To make this more concrete, imagine you have two systems, one that you use as a clock and one that you're studying. You don't actually need an external notion of time to describe their relationship. You can simply say that when the clock system is in one state, the other system tends to be in a certain state, and when the clock system changes, the other changes in a predictable way. Time, in this sense, is a bookkeeping tool for tracking correlations, not a fundamental ingredient. As these ideas have developed, some physicists have started to describe gravity itself as an emergent phenomenon. Instead of being a basic force, gravity might arise from statistical or informational principles, much like pressure arises from the collective motion of gas molecules. In this view, the bending of space-time is not a primary feature of the universe, but a large-scale effect of more microscopic processes. One proposal along these lines suggests that gravity is related to the flow of information and the tendency of systems to move towards states of higher entropy. When matter moves, it changes the way information is distributed, and the resulting patterns give rise to what we perceive as gravitational attraction. This is still a developing idea, and it is far from universally accepted, but it shows how far the conversation has moved from the traditional picture of space-time as a fixed foundation. There is also work in approaches like quantum gravity, where space-time is not smooth and continuous, but made of tiny discrete pieces, something like a fabric woven from individual threads. In these models, there is a smallest possible unit of area and volume, and the familiar continuum of space emerges only when you look at many of these units together. At that level, talking about a precise point in space or an exact moment in time no longer makes sense. The language we use for everyday distances and durations becomes an approximation, not a fundamental truth. String theory, another major line of research, offers yet a different perspective. In some versions of the theory, the basic objects are not points in space-time, but tiny vibrating strings or more abstract entities called branes. The geometry of space and time can depend on how these objects are arranged and how they interact. In certain mathematical formulations, space-time can even disappear entirely, replaced by a description that involves only algebraic relationships. What all of these approaches have in common is a quiet shift in what they treat as primary. Instead of starting with space and time and asking what lies inside them, they start with more abstract ingredients, like quantum states, information, or networks of relationships, and ask how the familiar notions of here and now could arise from those. It's important to say that none of this is settled. There is no single, agreed-upon theory that proves space-time is emergent. What exists instead is a growing collection of hints, mathematical results, and conceptual frameworks that all point in a similar direction. They suggest that the picture we have been using for over a century, where space-time is the deepest layer of reality, might be an effective description, not the final one. From a human perspective, this is both unsettling and strangely gentle. We build our lives around where we are and when we are. We mark our days by locations and moments, by meetings and milestones, by places we've been and times we remember. The idea that these might not be written into the universe at the most basic level can feel like the ground shifting slightly under your feet. At the same time, there is something calm about the thought that space and time could be like patterns on the surface of a deeper ocean. You don't need to see the entire ocean to float on its waves. In the same way, you don't need to understand the deeper structure of reality to live comfortably within the world of rooms and roads, mornings and evenings. As you sit here listening, your experience is still framed by a sense of position and a sense of sequence. The sound of this voice reaches you in time. Your body rests in space. those facts remain true at the level that matters for daily life. The questions scientists are asking now live many layers below that, in a realm of equations and models that most of us will never encounter directly. Still, it can be soothing to let the mind wander there, just a little, to imagine that beneath the familiar stage of space and time there might be a quieter structure, something made of connections rather than coordinates, of relationships rather than locations, a kind of invisible scaffolding that gives rise to the world we see, touch, and move through. As this line of thought continues, it naturally leads into deeper questions about what the universe is made of at its most basic level. If space-time is not the foundation, then what is? Is it information? Is it mathematics? Is it something we don't yet have a name for? These questions are not just technical puzzles. They shape how we think about reality, about our place in it, and about what it means to say that something exists. For now, you can simply rest with the notion that the floor beneath reality might be more like a woven net than a solid slab, and that the space around you and the time you feel passing could be gentle patterns rising from something deeper, something still waiting to be fully understood. Let your attention settle gently on a familiar name that has become almost synonymous with modern physics, Albert Einstein. You've probably heard his name spoken with a kind of quiet reverence, attached to images of wild hair, chalkboards filled with symbols, and ideas that bent the universe in ways no one expected. But tonight, instead of thinking about the man, let's focus on what his equations actually say about the world you're resting in right now, and what they might be quietly implying beneath their calm mathematical surface. Picture, for a moment, the simplest way you might describe motion. You are in a room. You take a step forward. You look at a clock. Something has changed in space, and something has changed in time. For most of human history, these two changes were treated as separate. Space was where things were. Time was when things happened. They were like two different coordinates on a map of experience, one telling you where to go, the other telling you when you arrived. Einstein's first great insight, known as special relativity, was that this separation doesn't hold up when you look closely at how light behaves. Light, it turns out, refuses to play by the usual rules of addition and subtraction. If you chase a beam of light, it doesn't slow down relative to you. It still moves away at the same speed. This simple, stubborn fact forces a strange conclusion. Space and time must adjust themselves depending on how you move. From this, a new picture emerged. Instead of a three-dimensional space that changes with a one-dimensional time ticking in the background, there is a single four-dimensional structure called spacetime. Every event, every flash of light, every heartbeat is a point in this four-dimensional world. Your life is not just a path through space, but a kind of thread woven through space-time itself. In this picture, the universe is not a stage where things happen. The stage and the happening are part of the same structure. What you call now is not a universal moment shared by everyone everywhere. It depends on how you are moving. Two people in different states of motion can disagree about whether two distant events happened at the same time, and both can be correct within their own frames of reference. This already shifts how we think about reality. But Einstein didn't stop there. About 10 years later, he introduced general relativity, a theory that takes this flexible space-time and gives it a new role. Instead of being just a passive arena, space-time becomes an active participant in the universe's behaviour. The core idea is surprisingly simple to state, even if it is mathematically demanding to work with. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. That sentence is often used as a kind of summary of general relativity, and it captures the mutual relationship at the heart of the theory. Imagine laying a heavy ball on a soft mattress. The ball creates a dip. Now roll a smaller ball nearby. It doesn't move in a straight line. It curves toward the larger ball, not because the big ball is pulling on it in the usual sense, but because the surface itself is curved. The smaller ball is simply following the shape of the mattress. In Einstein's view, gravity works in a similar way. A planet like Earth doesn't pull the moon toward it through an invisible force in empty space. Instead, Earth curves the space-time around it, and the moon follows the straightest possible path through that curved space-time. From our perspective, that path looks like an orbit. This idea is elegant, and it has been tested in countless ways. Light bends when it passes near massive objects. Time runs more slowly in stronger gravitational fields. The orbit of Mercury shifts in a way that Newton's equations can't fully explain, but Einstein's can. GPS satellites have to account for these effects, or your phone's map would quickly become inaccurate. So at this level, space-time appears to be a real physical thing. It can be curved, it can ripple, it can carry waves, known as gravitational waves, that travel across the universe when massive objects like black holes collide. In 2015, scientists detected these ripples for the first time, confirming yet another prediction of Einstein's theory. All of this makes space-time feel solid and fundamental. It seems to be the fabric everything else is stitched into, but if you look closely at the equations themselves, a subtle question begins to form. What exactly is space-time made of in Einstein's theory? In general relativity, space-time is described mathematically by something called a metric. The metric is a set of numbers that tells you how to measure distances and time intervals between nearby events. It encodes the geometry of space-time, the way lengths and durations are stretched or compressed depending on where you are and how much mass and energy are present. The equations of general relativity, known as the Einstein field equations, relate this metric to the distribution of matter and energy. On one side of the equation, you have terms that describe the curvature of space-time. On the other side, you have terms that describe the energy and momentum of whatever is in that space-time, such as particles, radiation, or fields. What is striking here is that space-time, in this framework, is treated as a smooth, continuous object. You can zoom in as far as you like, and the geometry is always well defined. There are no smallest pieces of space or time. There are no atoms of space-time. It is more like a perfectly elastic sheet that can be bent and twisted, but never torn into discrete chunks. This assumption works extremely well at the scales we can observe. But quantum mechanics, which governs the behaviour of particles at very small scales, paints a very different picture. In the quantum world, many quantities that seem continuous at larger scales turn out to come in discrete units. Energy levels in atoms are quantized. Light comes in packets called photons. Even fields have a grainy, fluctuating character when you look closely enough. This raises a natural question. If everything else becomes quantum and discrete at small scales, why should space-time remain smooth and continuous all the way down? What happens if you try to apply Einstein's equations at distances comparable to the so-called Planck length, a scale so tiny that it makes an atom look enormous by comparison? At that scale, the energy fluctuations predicted by quantum mechanics become so intense that they would drastically distort space-time itself. The smooth geometry assumed by general relativity would be overwhelmed by constant violent fluctuations. The very notion of a well-defined distance or a precise moment in time starts to lose meaning. This is one of the key places where the idea of space-time as a fundamental entity begins to wobble. Einstein's equations work beautifully in their domain, but they don't tell you what space-time is at the deepest level. They describe how it behaves, how it curves, how it responds to energy and momentum, but not what it is made of. You can think of it like the equations of fluid dynamics. Those equations describe how water flows, how waves move, how pressure and velocity change. They are extremely powerful, but they don't tell you that water is made of molecules. They treat the fluid as a continuous substance. The molecular structure only appears when you look at a different, deeper theory. In the same way, some physicists now wonder whether general relativity is a kind of fluid description of space-time. It tells you how the large-scale geometry flows and bends, but it may not reveal the underlying building blocks if there are any. This perspective is supported by an intriguing connection between gravity and thermodynamics, the branch of physics that deals with heat, energy, and entropy. In the 1990s, researchers discovered that Einstein's equations can be derived from principles that look very much like the laws of thermodynamics applied to horizons in spacetime, such as the event horizon of a black hole. In this approach, the geometry of spacetime behaves as if it has temperature and entropy, much like a physical system made of microscopic parts. This doesn't prove that spacetime is made of smaller components, but it suggests that thinking of it as a kind of collective statistical object might be fruitful. If spacetime has entropy, that implies it has many possible internal configurations, even if we can't see them directly. Entropy counts the number of ways a system can be arranged while still looking the same at a large scale. A gas in a box can be made of molecules arranged in countless microscopic patterns, all of which look like the same uniform cloud at a macroscopic level. By analogy, the smooth spacetime described by Einstein's equations might be the large-scale appearance of many underlying states. The equations themselves would then be describing an average behaviour, not a fundamental one. Another hint comes from the way general relativity handles energy. In most physical theories, you can define a local energy density, a way to say how much energy is present at a specific point in space. In general relativity, this becomes tricky. Because space-time itself is dynamic, and because gravity is not treated as a force in the usual sense, there is no simple, universally agreed upon way to define the energy of the gravitational field at a point. This suggests that the theory might be missing a deeper layer of description, one where concepts like energy and information are more clearly defined at a fundamental level, and space-time geometry emerges as a secondary feature. It's also worth noticing that Einstein's equations are classical. They do not include quantum uncertainty or superposition. They assume that spacetime has a definite shape at every point. But in the quantum world, physical systems can exist in combinations of states at once. If spacetime itself is a physical system, then a truly quantum theory of gravity would have to allow for spacetime to be in superpositions of different geometries. This is a strange idea to picture. It would mean that, at very small scales, the universe does not have a single, well-defined shape. Instead, it has many possible shapes that only settle into a familiar form when you look at large collections of events or average over many possibilities. From this viewpoint, the spacetime of Einstein's equations is like the smooth outline of a mountain range seen from far away. Up close, the landscape is jagged, irregular, full of details that the distant view smooths out. The equations give you the distant view. They don't show you the rocks and grains of sand. What makes this especially interesting is that the mathematics of general relativity is flexible enough to allow for very different kinds of underlying structures. The equations don't insist that spacetime must be fundamental. They simply take it as a starting point. You can, in principle, imagine a deeper theory where the basic ingredients are not points in space and moments in time, but something more abstract, like networks, graphs, or quantum states. In some modern approaches, spacetime is modelled as something that arises from a network of relationships between quantum systems. The connections in the network, rather than the positions of points, carry the fundamental information. Geometry then becomes a way of summarising the pattern of those connections. From that angle, Einstein's equations become an effective rule that describes how these patterns look and change when you view them at a large scale. They're not wrong, they're just not the whole story. It can be calming to think of it this way. The equations that govern planets, stars and galaxies are like the surface of a lake. They reflect light, carry waves, and support motion. Beneath that surface there may be a deeper structure, something more subtle and complex that only reveals itself when you dive down to the smallest scales. It might help to return briefly to your own experience. You feel located in a place. You feel carried along by a sequence of moments. These feelings are tied to the large-scale structure of space-time, the one Einstein's equations describe so well. At that level, the world is stable, predictable, and navigable. The questions physicists are asking now don't take that away. They don't make your chair less solid or your clock less useful. Instead, they invite a different kind of curiosity. They ask whether the familiar framework we use to organise our lives might itself be a kind of pattern, a summary of something deeper that we're only beginning to glimpse. Let's move forward from the gentle curves of Einstein's space-time into a much smaller, much stranger landscape, one where the rules you just settled into begin to slip, flicker, and behave in ways that don't quite line up with that smooth geometric picture. This is the realm of quantum mechanics, a framework that has been tested and confirmed with extraordinary precision, yet still manages to feel, even to the scientists who use it daily, like a kind of carefully organised mystery. To ease into it, think about something very simple. Imagine placing a small marble on a table. You can point to it. You can say where it is. You can roll it and watch it move along a clear, continuous path. This is the kind of world general relativity is built to describe. Objects have positions. They follow trajectories. Space and time provide a stage that, even if it can bend and stretch, remains a smooth backdrop for everything that happens. Now shrink that marble down until it becomes an electron. Suddenly the language you are using starts to fail. You can no longer say with certainty where the electron is, or how fast it is moving at the same time. Instead of a single, definite location, you have a cloud of possibilities. Instead of a clear path, you have a wave of probability. The electron doesn't travel like a tiny bead sliding along a line. It behaves more like a spread-out pattern that only snaps into a specific outcome when you interact with it. This is one of the core features of quantum mechanics. At a fundamental level, the theory does not describe what is happening in the same way classical physics does. It doesn't give you a precise story of how a system moves from one state to another. Instead, it gives you a mathematical tool that lets you calculate the likelihood of different outcomes when you make a measurement. This alone is already a shift in how we think about reality. But the real tension begins when you try to place this quantum world inside Einstein's space-time. In general relativity, space-time is a smooth, continuous entity. You can label every point with a set of coordinates. You can calculate how the geometry curves at each point. The equations assume that, at least in principle, these quantities are well defined no matter how closely you look. In quantum mechanics, by contrast, many quantities resist being pinned down so precisely. The uncertainty principle tells you that certain pairs of properties, like position and momentum, cannot both have exact values at the same time. The more precisely you know one, the less precisely you can know the other. If space-time itself is a physical entity, as general relativity suggests, then it should also be subject to quantum rules. That means there should be uncertainty in the geometry of space and time at very small scales. The shape of space-time should not be perfectly defined. It should fluctuate just like the energy and position of a particle. This idea leads to a kind of conceptual collision. General relativity wants space-time to be a stable, continuous fabric. Quantum mechanics wants everything to be fuzzy, probabilistic, and, at the deepest level, discrete. To see how this plays out, imagine trying to measure a very small region of space. According to quantum mechanics, the act of measuring something very precisely requires you to use a lot of energy. If you try to pinpoint a particle's position with extreme accuracy, you need a probe with a very short wavelength, which means very high energy. Now bring gravity into the picture. Energy, in general relativity, is what curves space-time. So if you concentrate a lot of energy into a very small region in order to make a precise measurement, you also strongly distort the space-time around that region. Push this idea far enough, and you reach a point where the energy you use to probe the space would create a tiny black hole, hiding the very region you are trying to observe. This suggests there is a fundamental limit to how finely you can probe space-time. Below a certain scale, the concept of a point in space may no longer make sense. The smooth fabric of space-time might dissolve into something more granular, or perhaps something even more abstract. This scale is often associated with the Planck length, which is about 10 to the minus 35 meters. It is an unimaginably small distance. If an atom were the size of the Earth, the Planck length would be smaller than a grain of sand by a similar factor. At this scale, the effects of quantum mechanics and gravity are expected to be equally important, and neither general relativity nor standard quantum theory can handle the situation on its own. From a mathematical point of view, the trouble shows up when physicists try to apply the usual techniques of quantum theory to gravity. For forces like electromagnetism, the strong force, and the weak force, there is a well-developed framework called quantum field theory. In this framework, fields fill space-time, and particles are seen as tiny excitations of those fields. The theory allows you to calculate probabilities for different processes, like particle scattering or decaying, with remarkable accuracy. If you try to treat gravity in the same way, by imagining a gravitational field made of tiny quantum particles called gravitons, the calculations quickly run into trouble. The equations produce infinities that cannot be neatly removed or renormalized. Unlike in the other forces, the theory loses its predictive power. It can no longer give you sensible answers. This mathematical breakdown is another sign that something deeper is going on. It suggests that gravity, and perhaps space-time itself, does not fit comfortably into the standard quantum field theory framework. The very idea of a field defined at every point in space-time might be part of the problem. There is also a conceptual tension in how the two theories treat time. In quantum mechanics, time is usually an external parameter. It is something you plug into the equations to describe how a system evolves. The system itself is described by a wave function that changes over time, but time is not part of the system. It is more like a background clock that ticks away independently. In general relativity, time is part of the system. It is woven into the geometry of space-time. It can slow down or speed up depending on gravity and motion. There is no single, universal clock that applies everywhere. If you try to describe the entire universe as a quantum system, this creates a puzzle. What is the clock you use to describe how the universe changes if time itself is part of the universe? This is one version of what physicists call the problem of time. Some approaches to quantum gravity lead to equations where time does not appear at all. The universe, in these formulations, is described by a static mathematical object, not something that evolves. The sense of change and flow that we experience has to be recovered in some indirect way, perhaps by looking at correlations between different parts of the system. This is a very different picture from the one we usually carry in our heads. We tend to think of the universe as something that exists in time, moving from past to future. These equations suggest that, at a fundamental level, the universe might simply be, and that time is something that emerges from how different parts of it relate to each other. Another place where the tension becomes visible is in the concept of locality. In general relativity, events are local. What happens at one point in space-time can only influence nearby points, and any influence travels at or below the speed of light. This is a deeply ingrained part of the theory. It is tied to the geometry of space-time itself. Quantum mechanics, through entanglement, seems to challenge this idea. When two particles are entangled, measurements on one can be correlated with measurements on the other, even if they are separated by large distances. No signal is travelling between them in the usual sense, but the connection is there nonetheless. This does not allow for faster-than-light communication, so it doesn't directly violate relativity, but it does suggest that the underlying structure of reality is not simply a collection of independent local pieces sitting in space-time. There are deeper, non-local connections that the space-time picture does not fully capture. When physicists try to combine these insights, they often find themselves questioning which parts of each theory are fundamental and which are effective descriptions. Is space-time a basic ingredient, or is it a useful way of organizing information about more fundamental quantum relationships? Is the wave function a complete description of reality, or just a tool for predicting outcomes? One way to think about this tension is to imagine two different maps of the same landscape. One map shows roads, cities and distances. The other shows weather patterns, temperatures and wind currents. Both maps are accurate in their own way, but they highlight different features and use different kinds of symbols. Trying to combine them into a single, unified map can be challenging, because the underlying assumptions about what matters and how things are represented are not the same. General relativity and quantum mechanics are like these two maps. One is geometric and continuous, the other is probabilistic and discrete. They both describe aspects of the same world, but they do so using very different languages. This becomes especially dramatic when you think about the early universe. According to Cosmology, the universe began in a state of extremely high density and temperature, often referred to as the Big Bang. In this regime, the gravitational field would have been incredibly strong, and quantum effects would have been significant. Neither general relativity nor standard quantum theory on their own can fully describe this situation. Similarly, at the centre of a black hole, general relativity predicts a singularity, a point where the curvature of space-time becomes infinite and the equations break down. Most physicists take this as a sign that the theory is being pushed beyond its domain of validity, and that a more complete quantum description of gravity is needed. These breakdowns are not just technical inconveniences, they are clues. They point to places where our current understanding of space-time and quantum reality is incomplete. They suggest that the two theories are not simply separate pieces that need to be glued together, but parts of a deeper framework that we have not yet fully uncovered. Over the years, many different approaches have been proposed to resolve this tension. String theory suggests that the fundamental objects are not point-like particles, but tiny vibrating strings. In this picture, space-time can emerge from the dynamics of these strings and the higher dimensional spaces they inhabit. Loop quantum gravity takes a different route, proposing that space-time itself is made of discrete loops or networks. The smooth geometry of general relativity emerges when you look at large numbers of these tiny building blocks together. Other approaches focus on information, entanglement, or more abstract mathematical structures. They explore the idea that what we call space and time might be secondary concepts, useful at large scales but not written into the deepest level of reality. What makes this particularly interesting is that, despite their differences, many of these approaches converge on similar themes. They suggest that space-time is not fundamental. They emphasize the role of relationships, correlations, and information. They treat geometry as something that can arise from more basic, non-geometric ingredients. From a philosophical point of view, this represents a shift in how we think about what the universe is made of. Instead of starting with a container, space and time, and then placing things inside it, we start with interactions and relationships, and let the sense of space and time grow out of those. As you let this idea rest in your mind, it might feel a little disorienting. Our everyday experience is so deeply tied to where we are and when we are, that it's hard to imagine a reality that doesn't begin with those concepts. But it can also be quietly fascinating to think that the familiar world of rooms and roads, mornings and evenings, could be like the surface of a deeper structure, something built from connections we don't directly perceive. At the same time, it's worth remembering that this tension between quantum mechanics and general relativity is not a failure of science. It is a sign of how far our understanding has come. We have two incredibly powerful theories that work extremely well in their own domains. The fact that they clash at the edges tells us where to look next. The search for a way to reconcile them is not just about finding a single, elegant equation. It is about rethinking some of our most basic assumptions about what space, time, and matter really are. It is about asking whether the stage we thought the universe was built on might itself be part of the performance. Somewhere far below the scale of anything you've ever seen, touched, or even imagined, there is a boundary that physics keeps running into, a kind of quiet line in the sand where the usual rules stop giving clear answers. You don't notice this boundary in daily life. It doesn't show up when you measure the length of a room, the weight of a cup of tea, or the time it takes for a song to finish. But in the equations that describe the universe, it sits there patiently, waiting for anyone who tries to look too closely. This boundary is known as the Planck scale, and it is named after the physicist Max Planck, who helped uncover the first hints that nature might not be as smooth and continuous as it appears. To ease into what this means, it helps to start with the idea of measurement itself, something so ordinary that we rarely stop to think about how strange it actually is. When you measure something, you're never just passively reading off a property that was already sitting there waiting for you. You're interacting with the thing you're measuring. You shine light on it, touch it with a ruler, bounce sound waves off it, or let it push against a scale. In every case, you exchange energy and information. The act of measuring is also an act of disturbance, even if the disturbance is usually so small that it doesn't matter. At large scales, this doesn't cause much trouble. You can measure the length of a table without noticeably changing the table. You can check the time on a clock without altering the way the clock works. But as you move towards smaller and smaller scales, this balance begins to shift. In the quantum world, this becomes impossible to ignore. To see something very small, you need to use a probe with a very short wavelength. Light with a long wavelength, like radio waves, will simply wash over tiny details without resolving them. To pick out fine structure, you need high frequency, high energy light, such as X-rays, or even more energetic forms of radiation. But high energy means strong interaction. When you hit a tiny particle with a very energetic photon, you don't just look at it. You kick it. You change its motion. You alter its state. The measurement and the system become entangled in a way that can't be cleanly separated. This is already a fundamental feature of quantum mechanics, but when you bring gravity into the picture, it takes on a new dimension. According to general relativity, energy and mass curve space-time. The more energy you concentrate in a small region, the more you bend the geometry around it. This means that the very tools you use to probe small distances, which require high energy, also begin to strongly affect the space-time you're trying to measure. If you imagine pushing this process to its extreme, you arrive at a strange conclusion. There is a point where trying to measure a smaller and smaller region of space requires so much energy that you would create a tiny black hole. Instead of revealing more detail, your measurement would hide the region behind an event horizon. The universe would, in a sense, close the curtain. This thought experiment suggests that there is a fundamental limit to how finely space can be probed. Below a certain scale, the concept of distance itself may lose its meaning. That scale is defined by a combination of three fundamental constants. The speed of light, which sets the maximum speed at which information can travel, Planck's constant, which sets the scale of quantum effects, and Newton's gravitational constant, which sets the strength of gravity. When you combine these numbers in just the right way, you get a length, a time, and an energy that mark the Planck scale. The Planck length is about 1.6 times 10 to the minus 35 meters. The Planck time, the time it takes light to travel one Planck length, is about 5.4 times 10 to the minus 44 seconds. These numbers are so small that they are difficult to compare to anything familiar. Even an atom, which already feels tiny, is enormous by comparison. What makes these scales special is not just their size, but what they represent. At these distances and times, the effects of quantum mechanics and gravity are expected to be equally strong. Neither theory can be ignored, neither can dominate. This is the regime where our current understanding runs out of clear guidance. Above the Planck scale, general relativity gives a smooth picture of space-time, and quantum mechanics can often be treated as a small correction. Below it, the very idea of a smooth space-time background becomes questionable. One way to picture this is to think about a digital image. From a distance, it looks like a continuous scene. You see gradients, curves, and smooth transitions. But if you zoom in far enough, you eventually see individual pixels. Below that scale, the idea of a smooth line or surface stops making sense. You're looking at the building blocks, not the image itself. Some physicists suspect space-time might be similar. At large scales, it looks like a smooth, continuous fabric. At very small scales, it may be made of discrete elements or more abstract structures that do not resemble space and time in the usual sense at all. This idea appears in several approaches to quantum gravity. In loop quantum gravity, for example, space is described as a network of tiny loops or links, often called spin networks. These networks have discrete units of area and volume. You cannot divide space indefinitely. There is a smallest possible chunk. In other approaches, space-time emerges from patterns of quantum entanglement or from mathematical structures that do not have a direct geometric interpretation. In these views, talking about a precise position or a precise moment at the Planck scale is like trying to talk about the exact location of a wave in the ocean. The description becomes more about relationships and correlations than about fixed coordinates. The limits of measurement at this scale are not just practical. They are built into the structure of the theories themselves. The uncertainty principle tells you that you cannot simultaneously know certain pairs of properties with arbitrary precision. When you apply this to space-time, it suggests that there may be a fundamental fuzziness in the geometry of the universe. Instead of a sharply defined point in space at a sharply defined moment in time, you might have a region of possibility, a small blur where different configurations overlap. The closer you try to zoom in, the more this blur resists being pinned down. This challenges a deeply ingrained assumption in physics, the idea that you can always, at least in principle, define what is happening at a single point in space-time. Many of our equations are built on this idea. Fields are defined at points. Particles move along paths that pass through points. Forces act locally at points. If points themselves lose their meaning at the Planck scale, then this whole way of describing the world needs to be rethought. There is also a connection here to the idea of information. In physics, information is not just an abstract concept, it is tied to physical systems. Storing a bit of information requires a physical state. Transmitting information requires energy and time. Some researchers have suggested that there is a maximum amount of information that can be packed into a given region of space. This idea comes, in part, from black hole physics. The entropy of a black hole, which is a measure of how much information it can contain, is proportional to the area of its event horizon, not its volume. This implies that, at a fundamental level, the number of degrees of freedom in a region of space might be limited. You cannot store infinite detail in a finite area. If that is true, then there is a natural limit to how finely the universe can be described. Below a certain scale, there simply aren't enough physical states to encode more detail. From this perspective, the Planck scale is not just a technical boundary, it is a kind of informational horizon. It marks the point where the universe runs out of room, so to speak, to define ever finer distinctions. This doesn't mean that nothing exists below the Planck scale. It means that our usual language of distances, durations, and positions may not be the right way to talk about whatever does exist there. The fundamental description might involve different kinds of variables, perhaps more abstract ones, that only give rise to space and time when you look at large collections of them. Another way to approach this is to think about how we define a clock. A clock is a system that changes in a regular, predictable way. You count those changes and use them to measure time. At everyday scales, this is straightforward. You can use the swing of a pendulum, the vibration of a quartz crystal, or the oscillations of an atom. But at the Planck scale, it is not clear what kind of physical process could serve as a clock. If space-time itself is fluctuating wildly, what does it mean for something to change in time? What does it mean for one event to happen before another, if the underlying notion of temporal order is uncertain? Some approaches to quantum gravity suggest that time, like space, may not be fundamental at this scale. Instead, it may emerge from relationships between quantum states. One system changes relative to another, and that relative change is what we interpret as the passage of time. This brings measurement back into the story in a different way. Instead of thinking about measuring space and time as if they were pre-existing containers, you start to think about measuring correlations between systems. You look at how one part of the universe behaves in relation to another, and from those patterns, you construct the idea of duration and distance. In this picture, the Planck scale is where the idea of an independent external ruler and clock stops working. You can no longer step outside the system and measure it from the outside. You're always part of the network of relationships you're trying to describe. It's also worth considering the practical side of this limit. Even with the most powerful instruments we can imagine, directly probing the Planck scale seems far beyond our reach. The energies required are many orders of magnitude higher than anything we can produce in laboratories, or even observe in the most energetic cosmic events. This means that much of what physicists say about this regime is based on mathematical consistency, theoretical arguments, and indirect clues from related phenomena like black holes and the early universe. It is a bit like trying to understand the structure of an ocean by studying the way waves behave at the surface. Yet, these indirect clues have been remarkably suggestive. The fact that so many different lines of reasoning point to a breakdown of the smooth space-time picture at very small scales has given researchers confidence that they are circling something real, even if the full shape of it remains elusive. There is a quiet humility in this part of physics. The Planck scale represents a reminder that our tools, both conceptual and experimental, have limits. No matter how advanced our theories become, there may always be a layer of reality that resists being cleanly translated into human language and measurement. At the same time, this boundary is also an invitation. It marks a frontier where new ideas are needed, where old assumptions can be questioned, and where entirely different ways of thinking about the universe might take shape. As you rest with this thought, you can notice how natural it feels, at a human level, to run into limits. You can only see so far into the distance before things blur. You can only remember so much detail before memories fade. You can only focus on so many ideas at once before your mind needs a pause. The universe, it seems, has its own version of this. There is only so much structure you can resolve before the very act of looking changes what you're trying to see, before the language of points and moments stops being useful. This does not make the world less real. It simply suggests that reality may have layers, and that the layer we are most familiar with, the one built from smooth space and flowing time, might be one of many. Beneath the calm, orderly picture of a universe laid out on a smooth grid of space and time, there is a growing suspicion among physicists that this neat geometry is only a surface appearance, a kind of large-scale approximation that begins to unravel when you look closely enough. The idea that space-time might be continuous, like an unbroken fabric, has served science extremely well for centuries. It allows for clean equations, precise predictions, and a mental picture that feels intuitive. But as measurements and theories push into ever smaller domains, that continuity starts to look less like a fundamental truth and more like a convenient illusion. To understand why this happens, it helps to return to the way we normally think about smoothness in the physical world. Take a wooden table, for example. Run your hand across its surface, and it feels flat and even. From a distance, it looks like a continuous plane. Yet if you were able to zoom in far enough, you would find a complex landscape of fibres, gaps, and irregular structures. The smoothness you experience is not a property of the smallest components. It is a property of how those components behave collectively at scales large enough for your senses to average over the details. Space-time, in the framework of general relativity, is treated like that tabletop surface, except it is assumed to be smooth all the way down. No matter how far you zoom in, the geometry is supposed to remain well defined. You can always talk about the curvature at a point, the distance between two events, the angle between two paths. This assumption underlies the entire mathematical structure of the theory. Quantum mechanics, however, brings with it a different way of looking at small scales. In the quantum world, smoothness is not the default. Instead, you find fluctuations, discrete jumps, and a kind of restless activity that never quite settles down. Even in what we would call empty space, quantum fields are constantly fluctuating. Particles and antiparticles can briefly appear and disappear. Energy levels shift and blur. When you try to combine these two pictures, a tension emerges. A smooth, well-defined geometry on one side. A fuzzy, fluctuating probabilistic world on the other. At everyday scales, this tension is easy to ignore. The quantum fluctuations are tiny, and the space-time geometry is gentle. But as you move towards smaller and smaller distances, those fluctuations become more significant. One way to see this is to think about the concept of a point in space. In classical geometry, a point has no size. It is an exact location, a precise coordinate. You can build lines, surfaces, and volumes out of these points, and everything fits together neatly. In quantum physics, the idea of an exact location becomes problematic. The uncertainty principle tells you that you cannot specify a particle's position and momentum at the same time with arbitrary precision. If you try to pin down where something is, you lose information about how it is moving. This is not a limitation of your instruments. It is a feature of how the world appears to work at a fundamental level. If particles do not have exact positions, then what does it mean to talk about a point in space-time? The geometry of general relativity assumes that you can, at least in principle, define fields and curvatures at exact points. But if the very idea of a point is blurred by quantum uncertainty, then the foundation of that geometry becomes shaky. This becomes even more pronounced when you consider the energy associated with quantum fluctuations. According to quantum field theory, every field has a certain amount of zero-point energy, even in its lowest possible state. This means that what we think of as empty space is actually filled with a background of restless activity. At large scales, the effects of this background mostly cancel out or become negligible. But at very small scales, the energy density of these fluctuations can become enormous. And in general relativity, energy density is what curves space-time. So, as you zoom in, you're not just looking at a smaller and smaller patch of a calm, smooth surface. You're looking at a region where energy and geometry are tightly linked, and where tiny changes in one can produce significant changes in the other. This leads to a picture sometimes described as space-time foam. Instead of a smooth fabric, the geometry at extremely small scales might be wildly fluctuating, constantly changing shape, forming and dissolving tiny structures. The notion of a fixed distance or a stable duration becomes difficult to maintain in such an environment. The foam metaphor is not meant to be taken too literally. It is a way of expressing the idea that the geometry itself is subject to quantum uncertainty. Just as a particle can be in a superposition of states, space-time might be in a superposition of different geometries. In such a scenario, there is no single, well-defined shape of space at the smaller scales. There is a range of possibilities, and the smooth geometry we experience is something that emerges when you average over many of these possibilities. Another angle on this breakdown comes from the way quantum field theory handles interactions. In these theories, particles interact by exchanging other particles, often visualized in terms of diagrams where lines meet at points. These interaction points are assumed to occur at specific locations in space-time. When you calculate the probabilities for different processes, you often have to integrate over all possible positions of these interaction points. At very small distances, these integrals can produce infinities, mathematical results that blow up instead of settling on a finite number. Physicists have developed techniques to deal with these infinities for most of the known forces, but gravity has stubbornly resisted these methods. The calculations suggest that treating gravity as just another quantum field defined on a smooth space-time background does not work at the deepest level. This is another hint that the smooth background itself might be part of the problem. If space-time is not fundamental, then building a theory that assumes it is fundamental and then trying to quantize everything else on top of it may be the wrong approach. There is also the issue of scale itself. In everyday language, we talk about small and large as if these are absolute categories. But in physics, scale is always relative to something else. A mountain is large compared to a person, but small compared to a planet. An atom is small compared to a grain of sand, but large compared to a proton. At the Planck scale, the usual reference points disappear. There is nothing smaller that we can meaningfully compare to. The very act of defining a scale becomes ambiguous. This suggests that the concept of distance might not be fundamental in the way we usually think it is. Some theoretical frameworks replace the idea of a smooth space with a network or graph. In these models, the basic elements are nodes and links, not points and coordinates. The links represent relationships or interactions between the nodes. Distance in this context is not a primary concept. It is something you define by counting how many links you have to traverse to get from one node to another. At large scales, such a network can look like a smooth space. Just as a large collection of discrete pixels can look like a continuous image, a dense network of connections can give rise to something that behaves like a geometric surface. At small scales, however, the discreteness becomes apparent. There is no meaning to talking about a location between two nodes. There is only the connection or the absence of it. This kind of picture aligns well with the idea that geometry might emerge from patterns of entanglement. In this view, the fundamental structure of reality is not a set of points in space, but a set of quantum systems that are related to each other in specific ways. The strength and pattern of those relationships determine how we perceive distances and shapes. If two systems are strongly entangled, they behave as if they are close together. If they are weakly entangled or not entangled at all, they behave as if they are far apart. Space, then, becomes a way of organizing these relationships into a form that is useful for large-scale description. This also offers a new way to think about why smooth spacetime works so well in everyday physics. At large scales, the network of relationships is dense and regular. The entanglement patterns are stable. The geometry that emerges from them is smooth and predictable. As you move to smaller scales, the network becomes sparser and more irregular. The patterns of entanglement fluctuate more strongly. The geometric picture starts to lose its clarity. Another important factor in this breakdown is the role of observers and measurement. In classical physics, you can imagine an observer who simply records what is happening without affecting it. In quantum mechanics, this is no longer the case. The act of measurement is an interaction that changes the system. If space-time itself is part of the quantum system, then measuring space-time is not a neutral act. Any attempt to probe the geometry at very small scales will disturb it. This makes it difficult to even define what it would mean to observe the true structure of space-time at those scales. This is one reason why some physicists emphasize operational definitions based on what you can actually measure with physical devices. From this perspective, space-time is not a thing that exists independently of measurement. It is a set of relationships between physical systems, such as clocks and rulers, and the processes that connect them. At large scales, different measurement procedures agree. Different clocks tick at predictable rates. Different rulers give consistent distances. This agreement gives rise to the idea of an objective shared space-time. At small scales, this agreement may break down. Different ways of probing the system might not lead to the same description. The concept of a single, well-defined geometry might no longer apply. There is also a deep connection between smoothness and symmetry. The space-time of general relativity is built to respect certain symmetries, such as the idea that the laws of physics should look the same at every point and in every direction. These symmetries are closely tied to conservation laws, like the conservation of energy and momentum. At very small scales, these symmetries might not hold in the same way. The underlying structure could be more irregular, with symmetries emerging only when you look at large collections of elements. This is similar to how a crystal works. At the level of individual atoms, the structure is discrete and anisotropic. There are preferred directions and patterns, but when you look at a large piece of the crystal, it can appear smooth and uniform. Space-time, in this analogy, would be like the large-scale appearance of a microscopic lattice. The smooth geometry is a macroscopic feature, not a microscopic one. What makes all of this especially intriguing is that it changes how we think about the role of geometry in physics. For a long time, geometry has been seen as the foundation. You start with a space, define distances and times, and then place fields and particles within that structure. In these newer perspectives, geometry becomes a product, not a starting point. You begin with something else: quantum states, information, networks of interaction, and then see how a geometric description arises as a useful way of summarizing their collective behavior. This reversal has practical consequences for how theories are built. Instead of trying to write down equations for a metric and then quantize it, researchers explore models where the basic variables are not geometric at all. They study how geometry can appear as an effective description in certain limits. This is not an easy task. Our mathematical tools and physical intuitions are deeply shaped by the idea of space and time as fundamental. Letting go of that idea, even temporarily, can feel like trying to think without using nouns. Still, the persistence of problems at very small scales has made this line of thought hard to ignore. The breakdown of smooth space-time is not just a speculative idea. It shows up in the mathematics, in the infinities, in the limits of measurement, in the behavior of black holes, and in the structure of quantum theory itself. From a broader perspective, this fits into a pattern that has appeared many times in the history of science. Concepts that once seemed basic and self-evident turn out to be emergent. Temperature, solidity, colour, even the idea of a rigid object, all make sense at human scales, but dissolve into different descriptions when you look at the microscopic level. Spacetime might be following a similar path. It is the natural way for beings of our size and complexity to organise experience. It is not necessarily the way the universe organises itself at the deepest level. Instead of asking, what is the smallest piece of space, you start asking, what are the basic relationships or processes that give rise to the feeling of space? That shift opens the door to thinking about reality in terms of connections rather than containers, interactions rather than locations. It suggests that the universe might be less like a box filled with things, and more like a web of relationships that, when viewed at the right scale, looks like a box with things in it. Moving forward from here, the conversation naturally turns toward what those underlying relationships might be made of. If smooth space-time is a large-scale appearance, then what is doing the appearing? Is it information? Is it quantum states? Is it something else entirely? Instead of beginning with a place or a scale, it helps this time to begin with a question about what you think the world is actually made of. If you were asked, casually and without much time to think, you might say it is made of things. Chairs, tables, air, people, planets, stars. If you pushed a little further, you might say atoms and then electrons, protons and neutrons. Push further still, and you might mention quarks, photons and other particles with names that sound like they belong in a quiet corner of a physics textbook. This way of thinking feels natural. We are surrounded by objects. We interact with them by touching, moving and seeing them. It makes sense to imagine the universe as a collection of tiny solid pieces, like an enormous, intricate mosaic built from fundamental tiles. Quantum theory invites you to slow down with that picture and look at it from a different angle. At its deepest level, the language of modern physics is not really about particles as little beads moving through space. It is about fields, patterns, and the way those patterns change and interact. To get a foothold here, it helps to think about something familiar. Consider the surface of a calm lake. The water itself is always there, even when nothing seems to be happening. If you toss a pebble into the lake, ripples spread outward. You can point to a ripple and follow it as it moves, but the ripple is not a separate object from the water. It is a pattern in the water. Quantum field theory, which is the framework that underlies our current understanding of particles and forces, treats the universe in a similar way. According to this view, what exists fundamentally are fields that fill all of space. These fields are always there, even in what we would call empty space. Particles are not independent objects moving through a void. They are localized excitations or disturbances in these underlying fields. There is an electron field, a quark field, a photon field, and so on. When the electron field is excited in a particular way, you observe what you call an electron. When the photon field is excited, you observe what you call a particle of light. This shift in perspective is subtle but profound. It means that emptiness is not truly empty. Even in the deepest vacuum you can create, the fields are still present, and they still fluctuate. These fluctuations are not just a mathematical curiosity. They have measurable effects. For example, two uncharged metal plates placed very close together in a vacuum will experience a tiny attractive force known as the Casimir effect. This happens because the quantum fields between the plates are constrained in a different way than the fields outside them, leading to a difference in energy that produces a physical force. So from this point of view, the fabric of reality is not made of isolated points or particles. It is made of continuous fields that exist everywhere, all the time, even when nothing seems to be happening. Now, place this picture alongside what you have been thinking about space-time. In general relativity, space-time is the stage, and matter and energy are the actors. In quantum field theory, the fields are the actors, and space-time is the stage on which the fields live and interact. This works remarkably well for most of the forces we know. The electromagnetic field, for example, is described by a quantum field theory that tells you how charged particles interact by exchanging photons, which are excitations of the electromagnetic field. The strong and weak nuclear forces are described in similar ways, with their own fields and their own particles. But gravity does not fit neatly into this picture. If you try to treat gravity as just another quantum field living on a smooth space-time background, the mathematics becomes unruly. The calculations produce infinities that cannot be handled in the usual way. The theory loses its ability to make clear predictions. This is another place where the idea that space-time might not be fundamental begins to quietly surface. Quantum field theory assumes that fields are defined at every point in space-time. It assumes that you can talk about what is happening here and here and here at arbitrarily small distances. If space-time itself breaks down at very small scales, then the idea of a field defined at every point also becomes questionable. The language of quantum field theory might be an effective description that works well when space-time is smooth, but not the final word. Even within quantum theory itself, the concept of a particle is more slippery than it first appears. In everyday experiments, particles seem like discrete objects. You see a dot on a screen where an electron hit. You see a flash in a detector when a photon is absorbed. It is tempting to imagine that the particle travelled along a definite path and arrived at that spot. The theory, however, tells a different story. Before the measurement, the particle is described by a wave function, which encodes a range of possible positions and outcomes. It does not say, the electron is here. It says, if you look, you are likely to find the electron here, or here, or here, with these probabilities. This wave function is not a physical wave in space, like a ripple on water. It is a mathematical object that lives in an abstract space of possibilities. When you perform a measurement, the range of possibilities collapses to a single outcome. There is still ongoing debate about what this collapse really means. Some interpretations say the wave function represents our knowledge, and the collapse is an update of that knowledge. Others say the wave function is a real physical entity, and the collapse is a real physical process. Still others suggest that all possible outcomes occur, each in its own branch of a larger reality. What matters for this discussion is that, in all of these interpretations, the simple picture of a particle as a tiny solid object moving through space-time is not fundamental. It is a useful way of summarizing what happens when quantum systems interact with measuring devices and produce definite outcomes. The deeper description is more about states, amplitudes, and probabilities than about positions and paths. There is another layer to this that becomes important when you think about how fields and space-time might be connected. In quantum field theory, the vacuum is not a state of nothingness. It is the lowest energy state of the fields. It is still full of structure. This vacuum structure can be different in different contexts. For example, an observer who is accelerating will see the vacuum differently from an observer who is at rest. What looks like empty space to one can look like a warm bath of particles to the other. This is known as the Unruh effect. Near a black hole, something similar happens. An observer far away sees the black hole emitting Hawking radiation, a faint glow of particles coming from the region near the event horizon. An observer falling into the black hole might see something very different. These effects show that the notion of a particle is not absolute. It depends on the observer and their state of motion. What one person calls a particle, another might call part of the vacuum. This blurring of the line between something and nothing, between particle and field, suggests that the underlying reality is not neatly divided into objects sitting in space. It is a more fluid structure, where what you observe depends on how you interact with it. If you now return to the idea that space-time itself might be emergent, this starts to fit into a larger pattern. Quantum theory describes the world in terms of states and their relationships. It does not require a fixed, pre-existing notion of space and time to define those states. In principle, you can talk about how quantum systems relate to each other, without embedding them in a geometric background. Some modern approaches to physics take this seriously, and try to build theories where the fundamental ingredients are quantum states and their interactions, not fields defined on a space-time grid. Geometry in these approaches becomes something that emerges from the structure of those interactions. One way to think about this is to imagine a large network of quantum systems, each one linked to many others through entanglement. The pattern of those links carries information about how strongly different parts of the network are related. If the network is highly connected in one region and less connected in another, you might interpret that as a region of space with a certain shape or size. Distance becomes a way of describing how many connections you have to traverse to get from one part of the network to another, rather than a measure of separation in a pre-existing space. In this picture, fields and particles are not things that live in space. They are features of the network itself. They are patterns of excitation and correlation within a web of relationships. This is a radical shift in language. Instead of saying, "There is an electron at this point in space," you might say, "There is a certain pattern of correlation between these parts of the network that, at large scales, we describe as an electron at this location." The everyday language of particles and positions is not wrong. It is just a translation of a deeper, more abstract description into terms that make sense at human scales. Another reason this shift matters is that it changes how we think about conservation laws and symmetries. In traditional physics, symmetries of space-time, like the fact that the laws of physics are the same at every point and in every direction, are closely tied to conservation laws, like the conservation of energy and momentum. If space-time is emergent, then these symmetries might also be emergent. They might arise from the structure of the underlying quantum relationships, rather than being fundamental features of the universe. This does not mean that energy and momentum stop being conserved in everyday situations. It means that, at the deepest level, these concepts might be approximations that become very accurate when you look at large numbers of degrees of freedom interacting in regular ways. There is also an interesting connection here to the role of mathematics in physics. The language of quantum theory is highly abstract. It involves complex numbers, vector spaces, operators, and other mathematical objects that do not have direct physical analogues in everyday experience. Space-time, by contrast, is something we can picture. We can imagine a line, a plane, a curved surface. Geometry feels tangible. If space-time is emergent, then the abstract mathematical structures of quantum theory might be closer to the fundamental description of reality than the geometric pictures we usually rely on. The universe, at its deepest level, might be more like a set of mathematical relationships than a physical stage. This idea can feel both unsettling and quietly elegant. It suggests that the solidity of the world we experience is not written into the universe in the most basic way. It is something that arises when a vast number of quantum systems interact in stable, predictable patterns. At the same time, it helps explain why the language of particles and fields works so well. It is the right language for describing those stable patterns at the scales we can observe and manipulate. Another layer of complexity comes from the way quantum theory handles interactions. When two particles interact, what is really happening in the field picture is that the underlying fields are influencing each other. The interaction is not a collision between two solid objects. It is a change in the pattern of excitations in the fields. These changes are described by mathematical expressions that calculate probabilities, not certainties. The theory tells you how likely different outcomes are, not which one will definitely occur. This probabilistic nature is not due to ignorance. It is built into the framework. Even if you knew everything there was to know about the initial state of a quantum system, you could still only predict the probabilities of different measurement results. This stands in contrast to the deterministic picture of general relativity, where, in principle, if you knew the exact state of space-time and matter at one moment, you could calculate how it would evolve. Bringing these two views together requires not just new equations, but a new way of thinking about what it means to describe the world. It may require a language that does not start with either a smooth space-time or a set of probabilistic fields, but something that can give rise to both. Some researchers explore the idea that information itself is the most fundamental concept. In this view, the basic building blocks of reality are not particles or fields, but bits of information, and the rules that govern how those bits can be transformed and shared. Quantum theory, with its focus on states and measurements, already has a strong informational flavour. Concepts like entanglement, entropy, and quantum communication treat physical systems in terms of what they can know about each other and how that knowledge can change. If space-time geometry can be derived from patterns of entanglement, as some theories suggest, then the bridge between fields, particles, and space-time might be built from information. This does not mean that the world is literally made of computer bits. It means that the relationships between physical systems, what can influence what can be known about what, might be more fundamental than the notion of where those systems are located. As you let this way of speaking settle, you can notice how different it feels from the everyday language of objects and places. It is less about things sitting in a container and more about a web of mutual influence. Still, the familiar picture does not disappear. When you wake up tomorrow, you will still see light coming through a window, feel the floor under your feet, and notice the time on a clock. The language of particles, fields, space, and time will continue to work extremely well for navigating the world. What changes is not the usefulness of that language, but our understanding of its depth. It becomes a surface description, a way of summarizing a much richer underlying structure. Long before you ever hear the word distance in a physics class, you already have a feeling for what it means. You know how far the kitchen is from the bedroom. You know the difference between a voice that's close and one that's calling from across a field. Distance in everyday life feels like a simple, solid fact. Things that are near can touch. Things that are far away cannot. Space in this sense acts like a quiet separator, placing objects into different locations and keeping them politely apart. Quantum entanglement invites you to sit with that idea for a moment and gently turn it over in your mind. It does not immediately deny the existence of distance, but it does suggest that distance might not be the whole story when it comes to how parts of the universe are connected. To begin, it helps to picture two small systems, such as two particles, created in a single interaction. In many quantum processes, particles are produced in pairs in a way that links their properties. For example, their spins, a kind of intrinsic angular momentum, might be related so that if one particle is measured and found to be pointing in a particular direction, the other will always be found pointing in the opposite direction. At first glance, this does not sound too strange. You might think the particles simply agreed on a plan when they were created. One goes this way, the other goes that way. The oddity appears when you realize that, according to quantum theory, the particles do not carry definite values for these properties before you measure them. Instead, they exist in a shared state, a single description that applies to both of them at once. This shared state can persist even if the particles are separated by a large distance. You can send one to one side of the planet and the other to the opposite side. When you measure one, the outcome you get is correlated with what will happen when the other is measured, even though no signal has had time to travel between them. This is what physicists call entanglement. It is not just a connection between two things, it is a description of the two as parts of a single combined system, no matter how far apart they are in space. This feature of quantum theory made even its early pioneers uneasy. Albert Einstein famously referred to it as spooky action at a distance. He did not like the idea that something could be influenced without any signal passing through the space between. Over the years, however, experiments have confirmed that these correlations are real. They cannot be explained by assuming that the particles carried hidden instructions from the moment they were created. The quantum description, where the system is treated as a single, inseparable whole, seems to be the one that matches what we observe. Now, it is important to say that entanglement does not allow you to send messages faster than light. You cannot use it to transmit information in a controlled way from one place to another. The outcomes of individual measurements are still random. What entanglement gives you is a pattern of correlation that only becomes clear when you compare results afterward. Even so, the existence of this pattern suggests something deep about how the universe is put together. It hints that, at a fundamental level, the idea of completely independent, separate systems might be an approximation. There are situations where the correct description is not this thing here and that thing there, but this combined system that happens to have parts we label as here and there. This is where the connection to space begins to take on a new shape. In the traditional picture, space is the primary organizer. You start with a set of locations, and then you place objects at those locations. Interactions happen because objects are near each other in space and can influence one another locally. Entanglement suggests a different starting point. It suggests that relationships between systems can exist that are not defined by their positions in space. The strength of the relationship is not measured in meters or kilometers, but in how tightly their quantum states are linked. Some physicists have taken this idea and asked a bold question. What if space itself is not the thing that defines which systems are close and which are far apart? What if it is the pattern of entanglement that defines the geometry of space? To see how this might work, imagine a large collection of quantum systems, such as a vast network of particles or quantum bits. Between these systems, there are many entanglement links of varying strength. Some pairs are strongly entangled, others are weakly entangled or not entangled at all. Now, suppose you try to draw a map of this network. You want to arrange the systems in a space so that the ones with strong entanglement links are placed near each other, and the ones with weak or no links are placed farther apart. If you do this carefully, you can produce a geometric picture where distance reflects the pattern of entanglement. In this picture, space is not something that exists first and then hosts entanglement. Space is something you build to represent entanglement. This idea has been explored in a variety of theoretical models, especially in the context of the holographic principle. In certain mathematical frameworks, a quantum theory without gravity, defined on a lower dimensional boundary, can be equivalent to a gravitational theory in a higher dimensional space. In these models, the geometry of the higher dimensional space is encoded in the pattern of entanglement in the lower dimensional quantum system. If you change how the quantum degrees of freedom are entangled, the shape of the space changes. This is not just a poetic analogy. There are precise mathematical relationships that connect measures of entanglement in the quantum theory to geometric quantities, like the area of certain surfaces in the gravitational description. From this perspective, entanglement acts like a kind of glue. It holds space together. Regions of space that are well connected by entanglement behave as a single, continuous area. If the entanglement between two regions is reduced, the space between them can effectively stretch or even tear apart. This way of thinking leads to a striking conclusion. The smoothness and continuity of space might depend on the density and structure of entanglement at the quantum level. A highly entangled network of quantum systems can give rise to a smooth geometric space. A less entangled network might correspond to a space that is more fragmented or disconnected. This connects back to the earlier idea that spacetime might break down at very small scales. If the fundamental structure is a network of relationships, then the familiar notion of a continuous distance only makes sense when there are enough connections to support it. There is also a natural link here to the idea of information. Entanglement is a form of shared information between systems. When two systems are entangled, information about one is, in a sense, encoded in the state of the other. If space is built from entanglement, then space is built from information. The geometry of the universe becomes a way of organizing how information is distributed and shared among its parts. This shifts the role of distance. Instead of being a primary feature of the world, distance becomes a measure of informational separation. Two regions are close if they share a lot of entanglement. They are far if they share very little. This idea can feel abstract, but it has concrete implications. For example, in a highly entangled system, disturbances can spread in a way that looks like signals travelling through space. The pattern of entanglement determines how quickly and in what way information can propagate. In a sense, what we call the speed of light might be related to how entanglement is structured in the underlying network. It sets a limit on how fast changes in one part of the system can influence another in a way that becomes observable at the level of particles and fields. There is also a connection here to black holes. In the context of entanglement-based models, the event horizon of a black hole can be seen as a region where the pattern of entanglement changes dramatically. The inside of the black hole and the outside become entangled in a very particular way, which is reflected in the geometry of the horizon. Some researchers have even suggested that certain types of entangled states might be equivalent, in a geometric sense, to tiny wormholes, connections between distant regions of space. This idea is sometimes summarized by the phrase ER equals EPR, referring to a proposed link between Einstein-Rosen bridges, which are wormholes, and Einstein-Podolsky-Rosen pairs, which are entangled particles. The suggestion is not that you can travel through these connections in any practical sense, but that the mathematical description of entanglement and the mathematical description of certain geometric features of spacetime might be two ways of talking about the same underlying structure. If this is correct, then what we think of as the connectivity of space is, at a deeper level, the connectivity of quantum states. This also offers a new way to think about why locality works so well in everyday physics. At large scales, the entanglement network is arranged in a way that produces a stable, well-behaved geometry. Systems that are nearby in space are also strongly entangled in the underlying description. Systems that are far apart are weakly entangled. This alignment between geometric distance and entanglement strength makes it possible to treat interactions as local. You can assume that what happens here mostly affects what is nearby, and only later influences what is far away. At smaller scales, or in more extreme situations, this alignment might break down. The pattern of entanglement might not map neatly onto a simple geometric picture. That could be another way of understanding why the smooth spacetime description begins to fail at very small distances, or near strong gravitational fields. There is also an interesting parallel here with how we think about networks in everyday life. In a social network, two people can be close in the sense that they share many mutual connections, even if they live on opposite sides of the world. Their closeness is not about physical distance, it is about the structure of their relationships. In an entanglement-based picture of space, physical closeness is like that. It is a way of summarizing how tightly different parts of the universe are linked at a deeper level. This analogy is not perfect, but it can make the abstract idea feel a bit more tangible. It suggests that space might be a map of connections rather than a container for objects. Another consequence of this view is that it changes how you think about the birth and evolution of the universe. In the early universe, shortly after the Big Bang, everything was packed into an extremely small region. In a traditional picture, this means that all points in space were very close together. In an entanglement-based picture, it could mean that the quantum systems that make up the universe were highly entangled with each other. As the universe expanded, the pattern of entanglement changed, giving rise to the growing geometry we describe as expanding space. This does not replace the standard cosmological description, but it offers a different way of interpreting what that description might be telling us at a deeper level. It also provides a new lens for thinking about the arrow of time. Entanglement tends to increase as systems interact. Two systems that start out separate can become entangled through interaction, but it is much harder in practice to make entanglement disappear completely. This growth of entanglement is closely related to the growth of entropy, the measure of disorder. If the structure of space is tied to entanglement, then the flow of time and the shape of space might be linked in subtle ways through the way information spreads and becomes shared across the universe. From a practical standpoint, entanglement has already moved out of the realm of pure theory and into technology. Quantum computers, quantum communication systems, and quantum sensors all rely on creating and manipulating entangled states. These technologies treat entanglement as a resource, something you can use to perform tasks that are impossible with classical systems alone. This reinforces the idea that entanglement is not just a strange theoretical curiosity. It is a real, physical feature of the world. As these technologies develop, they may also provide new ways to probe the deep structure of reality. Experiments with highly controlled quantum systems could, in principle, test some of the ideas about how entanglement and geometry are related, even if direct access to Planck-scale physics remains out of reach. All of this points toward a picture of the universe that is less about objects sitting in a pre-existing space, and more about a web of relationships that, when viewed at the right scale, looks like a space filled with objects. This does not mean that the everyday picture is wrong. It means that it is a translation, a way of summarizing a deeper, more abstract structure in terms that make sense for beings who live, move, and think at human scales. Two things can be far apart in space, and yet, at a deeper level, be part of a single, tightly connected system. Two things can be close in space and yet only weakly related in terms of their quantum states. The geometry you experience is one layer of description. The pattern of entanglement is another. Against the backdrop of everything you've been considering so far, there is one class of objects in the universe that seems almost purpose-built to test the limits of our understanding. A place where gravity, quantum theory, space-time, and information all press together until the usual boundaries between them begin to blur. These objects are black holes, and while they often appear in popular culture as simple cosmic vacuum cleaners, their role in modern physics is far more subtle and far more revealing. To approach them gently, it helps to begin not with the black hole itself, but with the idea of a horizon. In everyday life, a horizon is something familiar. It is the line where the sky seems to meet the land or the sea. You can walk toward it, but it always stays the same distance away. It marks the limit of what you can see from where you're standing. In physics, a horizon plays a similar role, but instead of limiting what you can see, it limits what you can be influenced by or what can influence you. An event horizon, the defining feature of a black hole, is a boundary in space-time. Once something crosses that boundary, it cannot send any signal back to the outside world. Not light, not a radio wave, not even a whisper carried by a particle. This already makes black holes strange. They carve out regions of the universe that are, in a very real sense, cut off from the rest. But what makes them especially important for the story you've been following is how they force physicists to confront the relationship between gravity and information. To see why, consider what happens when something falls into a black hole. From the outside, you can watch it approach the horizon. It appears to slow down, growing dimmer and redder as the light it emits is stretched by the intense gravity. Eventually it seems to fade away, frozen at the edge of the horizon. From the perspective of the falling object, however, nothing particularly dramatic happens at the horizon itself, at least for a sufficiently large black hole. It passes through in a finite amount of its own time and continues inward toward the centre. This difference in perspective is already a reminder that time and space behave in unfamiliar ways near strong gravity. But the deeper puzzle emerges when you ask a seemingly simple question. What happens to the information about the object that falls in? In physics, information is not just a metaphor. It refers to the complete specification of the state of a system. If you know the positions and motions of all the particles in a system, you have in principle all the information needed to predict its future behaviour. One of the foundational principles of quantum theory is that information is conserved. The evolution of a quantum system is reversible. Even if it becomes extremely complicated, the underlying information is not supposed to be destroyed. Black holes, at first glance, seem to violate this principle. According to classical general relativity, anything that falls into a black hole is lost to the outside world forever. All that remains from the perspective of an external observer is a black hole characterized by just a few simple properties: its mass, its electric charge, and its spin. This idea is sometimes summarized by the phrase, "black holes have no hair." No matter what complicated, detailed object you throw in, the black hole you get out looks the same, as long as the total mass, charge, and spin are the same. If that were the whole story, it would mean that all the detailed information about the object, its internal structure, its arrangement of particles, its history, would be erased. This would clash with the basic rules of quantum mechanics. For a long time, this was a serious problem. It suggested that either general relativity or quantum theory, or perhaps both, were incomplete. The situation changed in the 1970s when Stephen Hawking discovered something unexpected. Using a combination of quantum theory and the curved space-time around a black hole, he showed that black holes are not completely black. They emit a faint radiation, now called Hawking radiation. This radiation arises from quantum fluctuations near the event horizon. In the simplest picture, pairs of particles and antiparticles are constantly being created and annihilated in the vacuum. Near the horizon, it is possible for one particle of such a pair to fall into the black hole while the other escapes to infinity. To an outside observer, it looks as if the black hole is emitting particles. Over very long times, this process causes the black hole to lose mass and eventually evaporate. This discovery was remarkable for several reasons. It showed that black holes have a temperature. They obey laws of thermodynamics. They can be assigned an entropy. Entropy, as you may recall, is a measure of how many microscopic configurations correspond to the same macroscopic state. A system with high entropy can be arranged in many different ways internally, while still looking the same from the outside. The entropy of a black hole turned out to be proportional to the area of its event horizon, not its volume. This was a surprising result. It suggested that the number of internal states of a black hole, the amount of information it can contain, is tied to its surface, not to the region inside. This observation led to one of the most influential ideas in modern theoretical physics, the holographic principle. The principle suggests that all the information contained in a region of space can be represented by data on the boundary of that region. In the case of a black hole, the boundary is the event horizon. The detailed information about everything that has fallen in might be encoded in some way on that two-dimensional surface. This is a profound shift in perspective. It suggests that the three-dimensional world inside the black hole might be fully described by something living on a two-dimensional surface. More generally, it hints that the geometry of space itself might be a kind of projection from a more fundamental lower-dimensional description. Returning to the problem of information loss, Hawking radiation seems to make the situation even more puzzling at first. If a black hole evaporates completely, and all that remains is a cloud of radiation, where did the information about the original matter go? If the radiation is purely random, then the information is lost, and quantum mechanics is violated. If the radiation somehow carries the information out, then the black hole is not as simple and featureless as the no-hair idea suggests. Over the decades, a great deal of work has gone into resolving this puzzle. While the details are still being actively debated, there is now broad agreement among many physicists that information is not destroyed by black holes. Instead, it is somehow encoded in the correlations between the particles in the Hawking radiation. This means that, in principle, if you could collect all the radiation emitted by a black hole over its entire lifetime and analyze it with perfect precision, you could reconstruct the information about what fell in. What makes this especially interesting is how this conclusion connects to the idea that space-time and gravity might be emergent. If information is preserved, and if it is encoded on the horizon, then the interior of the black hole and the space-time geometry associated with it might be secondary descriptions of a more fundamental, information-based structure. This line of thought is supported by developments in string theory and holographic dualities. In certain mathematical models, a gravitational system in a region of space is equivalent to a quantum system without gravity living on the boundary of that region. In these models, black holes in the gravitational description correspond to certain high-energy, highly entangled states in the boundary quantum system. The entropy of the black hole matches the entropy of those quantum states. This provides a concrete example of how geometry, gravity, and information can be different ways of describing the same underlying reality. From this perspective, the event horizon is not just a physical boundary in space. It is a boundary between different descriptions of the same system. On one side, you have a picture in terms of curved space-time and falling objects. On the other side, you have a picture in terms of quantum states and their entanglement. The horizon marks the place where these two pictures meet. There is also a subtle connection here to the way entanglement works. Hawking radiation is entangled with the interior of the black hole. Each particle that escapes is, in a sense, linked to a partner that fell in. As the black hole evaporates, the pattern of entanglement becomes increasingly complex. The outgoing radiation becomes entangled not just with the interior, but with earlier radiation as well. This web of entanglement is thought to carry the information about the black hole's history. The geometry of space-time, including the presence of the horizon, may be a way of representing this complex structure of quantum relationships. Some researchers have taken this idea further and proposed that the smooth interior of a black hole might itself be a manifestation of entanglement. In this view, the connection between the inside and the outside, the continuity of space-time across the horizon, is supported by the entanglement between quantum states on either side. If that entanglement were somehow reduced or altered, the geometry might change. The horizon could become more like a barrier, or even something more dramatic, like a region of intense disruption. This line of thought leads into debates about what an observer falling into a black hole would actually experience. According to general relativity, they should pass through the horizon without noticing anything special, at least for a large black hole. Some arguments based on quantum information, however, suggest that the entanglement structure required to preserve information might lead to a breakdown of this smooth picture, potentially creating a highly energetic region at the horizon. These ideas are still being actively explored and contested. What matters for this conversation is that black holes have become a kind of a laboratory for testing ideas about the fundamental nature of space-time. They sit at the intersection of gravity, quantum theory, and thermodynamics. They force physicists to confront questions about what information is, how it is stored, and how it moves. Another important aspect of horizons is that they are not unique to black holes. There are other kinds of horizons in physics. For example, in an expanding universe, there can be a cosmological horizon. Beyond a certain distance, galaxies are moving away from us so fast that light emitted from them now will never reach us in the future. This means that there are regions of the universe that are, in practice, inaccessible to us, not because of a black hole, but because of the way space itself is expanding. These horizons also have thermodynamic properties. They can be assigned temperatures and entropies. This suggests that the connection between horizons, geometry, and information is a general feature of space-time, not something limited to black holes. In all of these cases, the presence of a horizon seems to create a link between the physics of space and time and the physics of information and entropy. The geometry of the universe and the way information is distributed within it are not independent. They are two sides of the same coin. This realization has influenced how physicists think about the laws of nature more broadly. Instead of seeing them as rules that govern objects moving in space and time, some researchers now see them as rules that govern the flow and transformation of information. In this view, space and time become part of the way information is organized and processed at large scales. They are not the ultimate backdrop, but a kind of interface that emerges from deeper informational dynamics. From a more intuitive angle, you can think about how this changes the story of what it means for something to be inside or outside. In everyday life, those are geometric concepts. They are about where something is located. In the context of black holes and information, inside and outside also become informational concepts. They are about which degrees of freedom are accessible to which observers, and how those degrees of freedom are correlated with each other. This adds a layer of subtlety to the idea of a boundary. The event horizon is not just a line in space, it is a line in the structure of what can be known and what can be influenced. This perspective can be extended beyond black holes. In any physical situation, what an observer can measure and what they cannot is determined by both the geometry of space-time and the structure of quantum information. This means that our description of reality is always, in part, a description of the relationship between the observer and the observed. The universe does not present itself as a single, complete picture that everyone can see in the same way. It presents itself through different windows shaped by horizons, motion, and the limits of measurement. All of this circles back to the idea that space-time might not be fundamental. If geometry is so tightly linked to information and entanglement, then it may be more accurate to think of space-time as a way of representing how information is organized in the universe, rather than as a basic ingredient from which everything else is built. Black holes in this sense are not just exotic objects at the edges of galaxies. They are signposts pointing toward a deeper understanding of what the universe is made of. They show that when gravity becomes strong and quantum effects become important, the familiar picture of a smooth, continuous space-time begins to give way to a description based on entropy, entanglement, and information. There is a certain kind of idea in physics that doesn't announce itself loudly at first. It doesn't arrive with a single, dramatic experiment or a sudden, obvious discovery. Instead, it slowly takes shape as different puzzles begin to point in the same direction, as if several quiet conversations across decades are gradually realizing they're all talking about the same thing. The holographic principle is one of those ideas, and to appreciate what it suggests, it helps to begin with something very ordinary. Think about a photograph. A photograph is flat. It has only 2 dimensions, and yet when you look at it you can see depth. You can tell which objects are closer, which are farther away. Your brain reconstructs a 3-dimensional scene from a 2-dimensional surface. The photograph does not contain the actual depth of the world it shows, but it contains enough information for your mind to create a convincing impression of it. A hologram takes this a step further. A true hologram is a thin surface that, when lit in the right way, produces the appearance of a fully 3-dimensional object floating in space. The depth you see is not really there in the usual sense. It is an effect created by how information is encoded on the surface. The holographic principle suggests that something similar might be true of the universe itself. It proposes that all the information contained in a volume of space can be represented on the boundary of that space. In other words, the 3-dimensional world you experience could, at a fundamental level be described by information living on a two-dimensional surface. This is not a metaphor meant to sound poetic or mysterious. It is a concrete claim about how the deepest description of physical systems might work. The roots of this idea trace back to the study of black holes and their entropy. As you've already explored, black holes have an entropy that is proportional to the area of their event horizon, not the volume of the region inside. This is unusual. In most physical systems, the amount of information or entropy scales with volume. A larger box can hold more gas molecules, more possible configurations, more information. A black hole seems to break this pattern. Its information content appears to be tied to a surface, not a space. This led physicists to wonder whether this was a special feature of black holes or a hint of something more general. Could it be that, in any region of space, the maximum amount of information that can be stored is determined by the area of its boundary, not by its volume? If that is true, then our usual way of thinking about space as something that holds information inside it might be backwards. Instead, the boundary might be the primary place where information is encoded, and the interior might be a kind of derived concept. To see how this idea gained traction, it helps to look at a specific and highly influential example from theoretical physics. In the late 1990s, a physicist named Juan Maldacena proposed a precise mathematical relationship between two very different kinds of theories. On one side of this relationship, there is a theory of gravity in a space with a certain kind of curved geometry, a universe with an extra spatial dimension. On the other side, there is a quantum theory without gravity, defined on the boundary of that space, which has one fewer dimension. What makes this remarkable is that these two theories, which look completely different on the surface, can be shown to be mathematically equivalent. Every physical process in the gravitational bulk theory can be translated into a corresponding process in the non-gravitational boundary theory, and vice versa. This is often described as a duality. It means you have two different languages for talking about the same underlying reality. In this particular case, the language of curved space-time, black holes, and gravity in the higher dimensional space is equivalent to the language of quantum fields, particles, and interactions on the lower dimensional boundary. From the point of view of the holographic principle, this is a powerful demonstration. It shows, at least in a specific mathematical setting, that a universe with gravity and space can be fully described by a theory that lives on its boundary and does not include gravity at all. This does not mean that our universe is exactly like the one in Maldacena's model. The geometry used in that example is highly symmetrical and not a perfect match to the universe we observe. But it provides a proof of concept. It shows that the idea of a holographic universe is not just philosophical speculation. It can be made precise, at least in some cases. What makes this especially interesting for the question of whether space-time is fundamental is the way geometry appears in these dual descriptions. In the boundary theory, there is no explicit notion of the extra spatial dimension that exists in the gravitational theory, and yet that dimension emerges when you translate the boundary description into the bulk description. In other words, a whole direction in space appears as a way of organizing information in a lower dimensional theory. The geometry of the higher dimensional world is encoded in the structure of the quantum states and their entanglement on the boundary. This ties directly into the earlier discussion about entanglement. In many holographic models, the shape of space in the bulk is closely related to how entangled the quantum degrees of freedom are on the boundary. There are specific mathematical tools that make this connection explicit. For example, certain geometric surfaces in the bulk theory correspond to measures of entanglement in the boundary theory. Change the pattern of entanglement, and the geometry changes. This strengthens the idea that space is not a fundamental arena in which things happen, but a way of representing how information is organized and shared in a quantum system. To make this feel a bit more tangible, imagine a very large and complex book. The story in the book describes a vast world, with landscapes, cities and characters moving through space. But physically, All of that information is encoded in patterns of ink on flat pages. The three-dimensional world of the story is not physically present in the book. It is something that emerges in the mind of the reader when they interpret the patterns on the page. The holographic principle suggests a similar relationship between the universe we experience and a deeper, lower-dimensional description. The pages are the boundary, and the story is the bulk space. This analogy has limits, of course. The universe is not literally a book, and there is no external reader. But it captures the idea that what looks like a three-dimensional spatially extended world might be encoded in something that, at a fundamental level, does not share that same structure. One of the more subtle implications of this idea is how it changes the role of gravity. In the holographic framework, gravity appears in the bulk description, but not in the boundary description. On the boundary, you have a quantum theory of fields and particles, but no gravitational force. This suggests that gravity might not be a fundamental interaction in the same way that the other forces are. It might be an emergent phenomenon, something that appears when you translate a non-gravitational quantum system into a geometric, space-time-based language. From this point of view, the curvature of space-time is not a basic ingredient of reality. It is a way of summarizing how the underlying quantum system behaves. This is a radical shift in perspective. It means that the geometry you experience, the feeling of being in a space that can be curved and stretched, might be a kind of large-scale visualization of more abstract, non-geometric processes. Another way to see the power of the holographic idea is to think about the limits of information storage. If the maximum amount of information in a region of space is determined by the area of its boundary, then the universe has a kind of built-in memory limit. You cannot pack infinite detail into a finite region. There is a maximum number of distinct states that region can have. This has implications for how we think about the continuity of space and time. If there is a finite limit to the amount of information in a given area, then you cannot define an infinite number of independent points within that area. The idea of a perfectly smooth, infinitely divisible space becomes questionable. Instead, space might be more like a grid or a network at the deepest level, with a finite number of degrees of freedom per unit area. The holographic principle does not tell you exactly what those degrees of freedom are. It does not give you a simple picture of what the boundary is made of. What it does is place a powerful constraint on how any fundamental theory of space-time and gravity must behave. It says that if such a theory exists, it must be possible, at least in principle, to describe it in terms of information living on a lower dimensional boundary. This has influenced a wide range of research in theoretical physics. It has provided new tools for studying strongly interacting quantum systems, new ways of thinking about black holes, and new perspectives on the nature of space-time itself. There is also a philosophical side to this idea that is hard to ignore. We are used to thinking of ourselves as living inside the universe, surrounded by space in all directions. The holographic principle invites a different mental picture, one where the deepest description of reality might be something like a cosmic boundary, and the world we experience is a kind of projection or reconstruction from that boundary. This does not mean there is literally a wall at the edge of the universe with information written on it. In many models, the boundary is not a physical surface you could travel to. It is a mathematical construct, a way of organizing the description of the system. Still, the idea that a lower dimensional description could be more fundamental than the higher dimensional one runs counter to everyday intuition. We usually think that more dimensions mean more complexity and more detail. Here, it is the opposite. The simpler, lower dimensional description is, in a sense, deeper. This inversion shows up in the way calculations are done. Sometimes, a problem that is extremely difficult to solve in the gravitational space-time-based description becomes much more manageable in the boundary quantum description. You can translate a question about black holes and curved space into a question about particles and fields on a flat surface, and then translate the answer back. This back and forth between descriptions is not just a mathematical trick. It suggests that what we call space and gravity might be like different coordinate systems for describing the same underlying physics. One of the most intriguing aspects of this is how it relates to the idea of emergence. In many areas of science, emergence refers to situations where complex, large-scale behaviour arises from simple, small-scale rules. Temperature emerges from the motion of molecules, pressure emerges from their collisions, a flock emerges from the interactions of individual birds. In the holographic picture, space-time emerges from the collective behaviour of quantum degrees of freedom on a boundary. The smooth geometry you experience is not present in the fundamental description. It appears when you look at the system at the right scale and in the right way. This aligns with the broader theme that has been developing throughout this exploration. The concepts that feel most basic to us, space, time, and even gravity, might be secondary. They might be the surface features of a deeper, more abstract structure built from information, entanglement, and quantum states. There is also an interesting connection here to how we think about causality. In a space-time-based picture, cause and effect are tied to the geometry. Signals can only travel within certain regions defined by light cones. What can influence what is determined by the structure of space and time? In a holographic picture, causality might be tied more directly to the structure of the quantum system on the boundary. The pattern of interactions and correlations there determines what kinds of processes can occur in the bulk. This raises subtle questions about whether the familiar notion of cause and effect is itself emergent, a feature of the geometric description rather than a fundamental rule. Another area where the holographic idea has had an impact is in the study of complex quantum systems, such as those found in condensed matter physics. Some of these systems are very difficult to analyse using traditional methods. The holographic duality provides an alternative approach, mapping the problem onto a gravitational system that can be easier to work with in certain respects. This cross-pollination between different fields of physics is one of the more practical outcomes of the idea. It shows that thinking about the universe in terms of boundaries and dual descriptions can lead to new tools and new insights, even in areas that are not directly about cosmology or black holes. At the same time, it is important to keep a sense of balance. The holographic principle, powerful as it is not a proven description of our entire universe. It is a well-established feature of certain mathematical models, and it has passed many internal consistency checks. But whether it applies in a direct way to the cosmos we observe is still an open question. What it does provide is a glimpse of a possible direction. It shows that it is logically consistent for a world with space, time, and gravity to be fully described by something that does not, at a fundamental level, include those concepts. That alone is enough to challenge the idea that spacetime must be the ultimate foundation of reality. You might notice how the story has gradually shifted from asking what space and time are made of to asking how information is organised. The focus has moved from geometry to encoding, from distances to relationships. The holographic principle is one of the clearest expressions of that shift. It takes the idea that information and entanglement might underlie space-time and gives it a precise mathematical form. Rather than starting with a place, a surface, or a distance, it can be grounding to begin this part with a state of possibility. In quantum theory, before anything is measured, before anything is said to be here or there, now or later, a system is described by what it could be, not by what it definitively is. This description lives in a mathematical space that does not look like the physical space you move through. It is a space of states, of amplitudes, of relationships between different potential outcomes. From within that abstract landscape, a question has slowly taken shape in modern physics. How does the familiar, geometric world of directions, distances, and shapes arise from something that does not seem to contain any of those features at all? To get a sense of why this question matters, it helps to recall how geometry usually enters the story. In most physical theories, you begin by assuming that space exists as a kind of background. You assign coordinates, you define distances, You talk about fields and particles living at specific locations. Geometry is the framework that everything else fits into. The idea being explored here turns that order around. It asks whether geometry itself might be something that comes later, something that appears when quantum systems are arranged and connected in certain ways. One way to approach this is to think about how you might describe a group of people who are connected by friendships. You could draw a map of where they live, marking each person's house on a street. That would give you a geometric picture of the group. But you could also draw a different kind of map, one that ignores physical location and instead shows who is friends with whom. In that map, people who talk a lot or share many connections would be drawn close together, even if they live far apart geographically. Both maps describe the same group of people, but they highlight different kinds of relationships. In some approaches to quantum gravity, the idea is that the friendship map of quantum systems, the pattern of how they are entangled and correlated, might be more fundamental than the geometric map of where they are in space. From this perspective, geometry is a way of translating patterns of quantum connection into a form that makes sense at large scales. Distance becomes a measure of how directly or indirectly systems are linked, not a primary feature of the world. To see how this plays out in more concrete terms, consider what a quantum state actually is. In the simplest sense, a quantum state is a mathematical object that encodes everything you can know about a system. For a single particle, this might include information about its possible positions, momenta, and other properties. For a large system, like a collection of many particles, the state includes information about all the possible ways those particles can be arranged and how their properties are correlated. When two systems are entangled, their combined state cannot be written as a simple combination of two independent states. The description of one system is tied to the description of the other. The state is a single, inseparable object. Now imagine a very large collection of quantum systems, each one entangled with many others. The full state of this collection is an enormously complex object, containing information about a vast web of correlations. Within that web, some systems will be more strongly connected than others. Some pairs will share a lot of information, others will be only weakly related. The idea that geometry can emerge from quantum states suggests that these patterns of connection can be translated into something that looks like a spatial structure. Systems that are strongly entangled appear close together. Systems that are weakly entangled appear far apart. This is not just a loose analogy. In certain mathematical models, especially those inspired by holographic dualities, there are precise formulas that relate measures of entanglement in a quantum system to geometric quantities in a corresponding spacetime description. For example, there are situations where the amount of entanglement between two parts of a quantum system is proportional to the area of a surface in a higher dimensional space. Change the entanglement and the area changes. In this way, a geometric feature is directly tied to a quantum property. This provides a concrete sense in which geometry can be seen as emerging from quantum states. The shapes and sizes you would measure in the spacetime description are reflections of how information is shared in the underlying quantum system. It is worth pausing on how different this is from the usual picture. Normally you would say that two particles are entangled because they are close enough to interact in space, or because they were created together at the same point in space and time. Space comes first and entanglement follows. Here, the order is reversed. Entanglement comes first, and space is something you infer from it. This shift has implications for how you think about the continuity of space. If space is built from patterns of connection, then smoothness depends on those patterns being dense and regular. When there are many connections linking many systems in a consistent way, the resulting geometry looks smooth. At smaller scales, where the network of connections might be sparser or more irregular, the geometric picture can become less clear. This fits naturally with the idea that smooth spacetime breaks down at very small distances. Another way to approach this is to think about how you might reconstruct a shape from a set of distances. Suppose you are given a list of distances between pairs of points, but you're not told where those points are located in space. With enough distance information, you can, in principle, reconstruct the shape of the arrangement. In the quantum case, the distances are not measured in meters. They are measures of entanglement or correlation. Given enough information about how strongly different parts of a system are linked, you can try to build a geometric picture that reflects those links. This is one of the goals of a field sometimes referred to as quantum geometry or emergent geometry. Researchers explore how to take a complex quantum state and extract from it a notion of shape, size, and connectivity. The fact that this is even possible in some models is striking. It suggests that geometry is not an independent ingredient that needs to be put in by hand. It can be derived, at least in certain contexts, from the structure of quantum states. There is also an important connection here to the idea of coarse graining. In physics, coarse graining means ignoring fine details and focusing on large-scale behavior. For example, when you describe a gas by its temperature and pressure, you're ignoring the individual motions of all the molecules and looking at an average description. The geometry you experience might be a kind of coarse-grained description of a much more detailed quantum state. At that deeper level, there may be no simple notion of position or distance. Those concepts appear only when you average over many degrees of freedom and look at the system from far enough away in a conceptual sense. This helps explain why geometry feels so solid and reliable in everyday life. The underlying quantum state of the universe is enormously complex, involving countless degrees of freedom. When you look at large collections of them together, stable patterns emerge. Those patterns can be described in geometric terms. In this view, a straight line, a flat surface, or a curved space is not a fundamental entity. It is a summary of how a vast number of quantum connections are arranged. This also offers a new way to think about motion. In a traditional picture, an object moves through space over time. It follows a path, a world line, in space-time. In an entanglement-based picture, motion can be seen as a change in the pattern of connections. As a system interacts with its surroundings, the way it is entangled with other systems changes. That changing pattern, when translated into geometric language, looks like movement through space. This is a subtle shift, but it has interesting consequences. It suggests that what you perceive as an object travelling from one place to another might be, at a deeper level, a continuous reshaping of its relationships with the rest of the universe. Another layer to this story comes from the role of symmetry. In physics, symmetries are deeply tied to conservation laws. The fact that the laws of physics look the same everywhere in space leads to the conservation of momentum. The fact that they look the same at all times leads to the conservation of energy. If geometry is emergent, then these symmetries might also be emergent. They might arise from regularities in the underlying quantum state. This does not mean that conservation laws suddenly stop working. It means that, at the deepest level, they might not be written into the fabric of reality as fundamental rules. They might be properties of a particular class of quantum states, the ones that give rise to a stable, smooth geometry. This idea is still being explored, and it is not without challenges. One of the difficulties is that the mathematical tools needed to describe large, strongly entangled quantum systems are extremely complex. Even with modern computers and sophisticated techniques, fully characterizing such states is a daunting task. Despite this, progress has been made in simplified models. For example, researchers study systems made of quantum bits arranged in networks, sometimes called tensor networks. These are mathematical structures that make it easier to describe how large quantum states are built from smaller pieces. In certain cases, the structure of a tensor network has a clear geometric interpretation. The way the network is connected can be drawn as a kind of curved space. The depth of the network corresponds to an extra spatial dimension. The entanglement between different parts of the system is represented by the links in the network. This provides a tangible example of how geometry can emerge from a purely quantum description. The network itself is not a space, it is a mathematical object. But when you look at its structure in the right way, it gives rise to something that behaves like a geometric space. These models are not perfect representations of the real universe, but they serve as laboratories where ideas about emergent geometry can be tested and refined. Another aspect of this story involves the role of observers. In quantum theory, what you observe depends on how you interact with the system. The state of a system is not just a property of the system alone. It is a description of how the system relates to the observer and the measurement process. If geometry is derived from quantum states, then the geometry you perceive might also depend, in some subtle way, on the kinds of measurements and interactions you are capable of making. This does not mean that everyone lives in a different space. At large scales, the geometry is robust. Different observers agree on distances and shapes to a high degree of precision, but at very small scales, or in extreme conditions, there might be multiple, equally valid geometric descriptions, corresponding to different ways of slicing up the underlying quantum state. This is a challenging idea, because it pushes against the notion of a single, objective space-time that exists independently of any observer. Instead, space-time becomes something like a shared interface, a way of organizing experience that emerges from a deeper observer-independent quantum reality. There is also an interesting connection here to the arrow of time. If geometry emerges from the structure of quantum states, then the flow of time might be tied to how those states change and become more entangled. In many physical processes, entanglement tends to increase. Systems that start out separate become linked through interaction. This increase in entanglement is closely related to the increase in entropy. If the shape of space is tied to entanglement, then the evolution of space and the flow of time might be two aspects of the same underlying process: the spreading and restructuring of information across the quantum state of the universe. This offers a different way to think about cosmology. The expansion of the universe, usually described in terms of galaxies moving apart in space, might also be described as a change in the pattern of entanglement among the universe's fundamental degrees of freedom. Again, this does not replace the standard cosmological picture. It adds another layer of interpretation, one that looks beneath the geometric description and asks what it might be summarizing. Another point worth considering is how this view affects the idea of locality. In a geometric picture, locality is about nearness in space. Systems that are close can interact. Systems that are far apart cannot, at least not directly. In an entanglement-based picture, locality is about the strength of quantum connections. Systems that are strongly entangled can influence each other in subtle ways, even if they are far apart in the emergent geometric sense. At large scales, these two notions tend to align. Strong entanglement usually corresponds to geometric closeness, but at deeper levels the alignment might not be perfect. This could help explain some of the puzzling features of quantum theory, where non-local correlations appear without violating the basic rules of causality. It also suggests that the familiar idea of a light cone, the region of space-time that can influence or be influenced by a given event, might itself be an emergent concept, a feature of the geometric description rather than a fundamental limit built into the underlying quantum system. As you reflect on this, it can be helpful to keep in mind that these ideas are still very much at the frontier of research. There is no single, agreed-upon theory that fully explains how geometry emerges from quantum states in our universe. What exists instead is a growing collection of models, examples, and partial results that all point in a similar direction. They suggest that the relationship between quantum theory and space-time is not one where you simply take a fixed geometry and add quantum rules to it. It is one where geometry itself might be a product of quantum rules. This changes the way physicists think about what a theory of everything might look like. Instead of a single set of equations written on a space-time background, it might be a set of rules for how quantum information is structured and transformed, from which space, time, and gravity all follow as effective descriptions. There is something quietly elegant about this possibility. It suggests that the complexity of the universe, the vast sweep of galaxies, and the delicate structure of atoms might all be different expressions of the same underlying web of relationships. At the same time, it is a humbling thought. It implies that the world as we experience it, with its clear sense of here and there, before and after, might be a kind of translation, a way of making sense of something that is, at its deepest level, written in a very different language. Consider for a moment something as simple as warmth spreading through a room. You turn on a heater, and over time the air becomes more comfortable. No single molecule of air decides to carry heat from the heater to the far corner. Instead, countless tiny collisions between molecules gradually distribute energy throughout the space. The warmth you feel is not a fundamental force acting between objects. It is a collective behaviour, a large-scale effect that emerges from many small local interactions. Some physicists have begun to wonder whether gravity might be similar in spirit, not a basic interaction written into the deepest layer of reality, but a large-scale emergent behaviour that arises from the way information and entropy are organised in the universe. To appreciate how this idea takes shape, it helps to revisit what thermodynamics is really about. Thermodynamics does not concern itself with individual atoms or molecules. It deals with averages. It talks about temperature, pressure, and entropy, quantities that only make sense when you're looking at many particles together. Entropy, in particular, is a measure of how many microscopic arrangements correspond to the same macroscopic appearance. A neatly arranged deck of cards has low entropy. There are only a few ways to arrange it so that it looks ordered. A thoroughly shuffled deck has high entropy. There are many, many ways to arrange the cards so that they look random. In physical systems, entropy tends to increase. This is the essence of the second law of thermodynamics. Systems naturally evolve towards states that can be realized in many different microscopic ways. Now, connect this to gravity. Traditionally, gravity is described as a force between masses, or, in Einstein's language, as the curvature of space-time caused by energy and matter. This description is geometric and local. It tells you how objects move in response to the shape of the space around them. The thermodynamic perspective asks a different kind of question. Instead of starting with forces or geometry, it starts with information and entropy. It asks how the number of possible microscopic configurations of a system changes as objects move and interact. One of the first hints that gravity and thermodynamics might be connected came from the study of black holes. As you've already seen, black holes have entropy. They have a temperature. They obey laws that look remarkably like the laws of thermodynamics. The area of a black hole's event horizon plays the role of entropy. The surface gravity at the horizon is related to temperature. When matter falls into a black hole, the total entropy, including the entropy of the black hole itself, increases. This parallel is not just a loose analogy. There are precise mathematical relationships that make the connection exact. Black holes behave in many respects like thermodynamic systems. This raises a natural question. If gravity, at least in the context of black holes, has a thermodynamic character, could that be true more generally? Could the equations that describe gravity be derived from thermodynamic principles? In the mid-1990s, a physicist named Ted Jacobson explored this idea in a striking way. He showed that, under certain assumptions, you can derive Einstein's field equations, the equations of general relativity, from a relationship that looks like the first law of thermodynamics, the law that relates changes in energy, temperature, and entropy. The basic idea is to imagine that every point in space-time has an associated horizon, similar to a black hole horizon, but on a very small local scale. You then apply thermodynamic reasoning to these horizons, relating the flow of energy across them to changes in entropy and temperature. From this reasoning, the familiar equations that describe how space-time curves in response to energy and matter emerge naturally. This result does not prove that gravity is thermodynamic in the same way that heat is, but it suggests that there is a deep and non-accidental connection between the two. Another approach to this idea focuses more explicitly on information. In physics, information is tied to the number of possible states a system can be in. More information means more possible configurations. Some researchers have proposed that what we call gravity is actually a manifestation of how information is distributed in space. One version of this idea suggests that when a mass moves, it changes the way information is arranged in the surrounding region. This change creates an effective force that we interpret as gravity. To make this a bit more concrete, imagine a surface that encodes information about the positions of objects in a region. If an object moves closer to the surface, the amount of information that needs to be stored on that surface changes. The system tends to evolve in a way that increases the total entropy, and this tendency can look like an attractive force. In this picture, gravity is not something that objects do to each other. It is something that happens because the universe as a whole is moving towards states with higher entropy. This is a radical departure from the traditional view. It replaces the idea of a fundamental gravitational interaction with the idea of an entropic force, a force that arises because of statistical tendencies rather than direct interactions. There are familiar examples of entropic forces in everyday life. Consider a polymer chain, like a long molecule floating in a liquid. The chain tends to coil up, not because there is a direct force pulling its ends together, but because there are many more microscopic configurations where the chain is coiled than configurations where it is stretched out. The tendency to move toward the more probable higher entropy states creates an effective force. In this analogy, gravity would be like the coiling of the polymer. Objects move toward each other not because they are fundamentally attracted, but because that arrangement corresponds to a higher entropy configuration of the underlying degrees of freedom. This idea has been developed in various ways, and it remains controversial. Not everyone is convinced that it can fully account for all the features of gravity, especially in dynamic, time-dependent situations. Still, it fits naturally with the broader theme that geometry and forces might be emergent rather than fundamental. There is also a connection here to the role of horizons and observers. In thermodynamics, temperature is often associated with a lack of information. A system at a certain temperature is one where you do not know the exact microscopic state. You only know an average. In the context of gravity, horizons limit what an observer can know. An observer outside a black hole cannot access information about what is inside. This lack of access is associated with entropy and temperature. Some researchers have suggested that gravity itself might be linked to these limits on knowledge. The way space-time curves could be related to how information is hidden or revealed to different observers. This adds a relational aspect to gravity. Instead of being a property of space-time alone, gravity becomes a feature of the relationship between observers, information, and the systems they are observing. Another line of thought connects gravity to the idea of coarse-graining. When you describe a system at a large scale, you ignore many microscopic details. You group many different underlying states into a single macroscopic description. Geometry and gravity might be part of this coarse-grained description. They might be the natural language for talking about the large-scale behavior of a system whose fundamental description is in terms of quantum states and information. From this point of view, trying to quantize gravity by treating space-time geometry as a fundamental quantum field might be like trying to describe the temperature of a gas in terms of the quantum states of a single molecule. You're mixing levels of description. Instead, you might need to start with a theory of quantum information and then derive geometry and gravity as effective, large-scale concepts. This perspective also offers a different way to think about why gravity is so weak compared to the other fundamental forces. If gravity is not a fundamental interaction, but an emergent effect, its relative weakness might be a natural consequence of the fact that it only appears at large scales when many degrees of freedom are involved. The electromagnetic, strong and weak forces operate directly at the level of particles and fields. Gravity, in this picture, would operate at the level of collective behavior. This idea has not yet been turned into a complete predictive theory that can be tested in the same way as general relativity or quantum field theory. But it has influenced how many physicists think about the problem of quantum gravity. It has encouraged them to look for principles that govern information entropy and entanglement, and to see geometry and forces as consequences of those principles rather than as starting points. There is also an interesting connection here to cosmology. The universe as a whole has an entropy, and that entropy appears to be increasing over time. The expansion of the universe, the formation of structures like galaxies and stars, and the growth of black holes all contribute to this increase. If gravity is tied to entropy, then the large-scale evolution of the universe might be driven, in part, by informational and thermodynamic considerations, rather than just by geometric ones. This does not mean that the equations of general relativity are wrong. They work extremely well for describing the motion of planets, the bending of light, and the dynamics of galaxies. In this view, they are like the equations of fluid dynamics, which work extremely well for describing the flow of water, even though water is made of molecules. The equations capture the effective large-scale behaviour of a deeper, more detailed system. Another aspect of this idea involves the arrow of time. Thermodynamics is deeply connected to the direction of time. The second law, which states that entropy tends to increase, gives time a direction. It distinguishes the past from the future. If gravity is linked to entropy, then the flow of time and the behaviour of gravity might be connected in a fundamental way. The way spacetime evolves could be tied to the way information spreads and becomes more distributed. This opens up a different way of thinking about why time seems to move forward. Instead of being a basic feature of the universe, the direction of time might be a reflection of how the universe's information content is arranged and how it changes. There is also a conceptual elegance to this idea. It unifies several strands of thought that have appeared throughout this exploration. Entanglement, information, horizons, geometry, and now gravity all begin to look like different aspects of the same underlying structure. In this unified picture, the universe is not primarily a collection of objects moving through a pre-existing space under the influence of forces. It is a vast, evolving network of information with patterns of connection and correlation that, when viewed at large scales, appear as space, time, and gravity. This is a very different way of telling the story of the cosmos. It replaces the image of a mechanical universe, governed by pushes and pulls, with the image of a statistical universe, governed by patterns, probabilities, and the flow of information. At the same time, it does not make the world feel less real. The warmth you feel from the heater is still warm. The pull of the earth still keeps your feet on the ground. The equations of gravity still predict the motion of the planets with extraordinary accuracy. What changes is the interpretation of what those equations are really describing. They become, in this view, the surface features of a deeper, more abstract reality. There is something quietly human about this shift. We often start by describing the world in terms of things we can touch and see. As our understanding deepens, we move toward descriptions in terms of relationships, patterns, and information. Physics, in this sense, mirrors the way we learn about each other. We begin with appearances and actions. Over time, we come to care more about connections, histories, and the invisible threads that link one person to another. As this line of thought continues, it naturally leads to a question about time itself. If gravity and geometry might be emergent, tied to information and entropy, then what about the flow of time? Is time a fundamental river that everything drifts along, or is it too a feature that arises from the way the universe's information changes? Begin for a moment by noticing the most ordinary signal of time in your own surroundings. It might be the soft hum of a device, the rhythm of your breathing, or the faint awareness of light changing outside a window. None of these things announces itself as time in any official way, and yet each one gives you a sense that something is moving forward, that one moment is giving way to the next. You do not experience time as a number on a clock first. You experience it as change. This simple observation turns out to be a quiet doorway into one of the deepest questions in modern physics. What if time, at the most fundamental level, is not a built-in feature of the universe, ticking away in the background like an invisible metronome? What if it is something that only appears when systems change in relation to each other? In everyday life, clocks feel like the most basic tools imaginable. You look at a watch or a phone, and there it is. A clear display of hours, minutes, and seconds. It feels as though the clock is revealing a universal truth, a single timeline that everyone shares. Physics, especially in its more advanced forms, tells a subtler story. Even in Einstein's theory of relativity, time is not universal. Two observers moving at different speeds, or sitting in different gravitational fields, will disagree about how much time has passed between the same pair of events. Time is woven into space-time, shaped by motion and gravity. Quantum theory pushes this strangeness even further. In many of the equations that describe quantum systems, time appears not as a physical quantity to be measured, but as an external parameter, something you use to label how a system changes, not something the system itself contains. This difference becomes especially sharp when you try to describe the entire universe as a quantum system. If the universe is everything that exists, then there is nothing outside it. There is no external clock you can refer to in order to say how the universe is changing. The usual role of time in the equations becomes ambiguous. This leads to what physicists often call the problem of time. In some attempts to combine quantum mechanics and general relativity into a single framework, the fundamental equations do not include time at all. They describe a static mathematical object, a kind of timeless state that encodes all possible configurations of the universe. From this perspective, the universe, at its deepest level, does not evolve. It simply is. At first, this sounds completely at odds with experience. You feel time passing. You remember the past. You anticipate the future. The idea that the fundamental description of reality might not include time seems to conflict with the most basic features of conscious life. The key to resolving this tension may lie in the idea of relational time. Instead of thinking of time as something that exists independently, you think of it as something that emerges from the relationships between systems. To see how this works, imagine two simple systems. One is a pendulum swinging back and forth. The other is a light that can turn on and off. You can describe the behavior of the light in terms of the pendulum. When the pendulum is at the left, the light is on. When the pendulum is at the right, the light is off. You do not need an external clock to make sense of this description. You're not saying that the light turns on at a certain number of seconds. You're saying that the light turns on when the pendulum is in a certain state. In this way, the pendulum acts as a clock for the light. Time is not a separate entity. It is a way of describing the correlation between the states of two systems. Now, scale this idea up to the universe as a whole. Instead of a single pendulum and a single light, you have countless systems, all interacting, all changing. You can pick some of them and use them as reference systems, as clocks, to describe the behavior of the others. The flow of time, in this view, is not something that exists independently. It is something you construct by tracking how different parts of the universe change in relation to each other. This relational idea fits naturally with the broader theme that space and geometry might also be emergent, just as distance can be seen as a way of summarizing how strongly systems are connected. Time can be seen as a way of summarizing how systems change together. There is also a strong connection here to the concept of entropy. As you explored earlier, entropy is a measure of how many microscopic configurations correspond to the same macroscopic appearance. It tends to increase over time in isolated systems. This increase in entropy gives time a direction. It distinguishes the past from the future. A broken glass does not spontaneously reassemble itself. A mixed-up deck of cards does not naturally return to perfect order. In a world without a fundamental clock, this arrow of time might be one of the key features that makes time feel real to us. Instead of being driven by an underlying ticking, the sense of flow could be driven by the way information spreads and becomes more distributed. From this perspective, the past is the set of states with lower entropy, fewer possible configurations. The future is the set of states with higher entropy, more possible configurations. The feeling that time moves forward is tied to the fact that the universe tends to move towards states that can be realized in more ways. This idea can be linked back to quantum entanglement. As systems interact, they tend to become entangled. Their states become correlated in more complex ways. This growth of entanglement is closely related to the growth of entropy. If the structure of space is tied to patterns of entanglement, and the flow of time is tied to the growth of entanglement, then space and time begin to look like two aspects of the same underlying process, the way information is structured and transformed across the universe. There is also a subtlety here about memory and records. When you remember something, you're not accessing the past directly. You're accessing a physical record in your brain, a pattern of neural connections that was shaped by earlier events. Similarly, photographs, written notes, and geological layers are all physical systems that carry information about earlier states of the world. In a relational picture of time, these records are part of what creates the sense of a past. The universe contains systems that encode information about other systems in earlier states. The web of these records and correlations gives rise to a consistent story of what has happened. This can be framed in a very simple way. The present is the collection of all the information that exists right now. The past is the subset of that information that refers to earlier states. The future is not encoded yet. It is open, in the sense that it has not left physical traces. This way of thinking does not require a fundamental clock. It requires only that the universe has a structure that allows information to be stored, copied, and transformed. Another angle on this comes from the study of quantum cosmology, where physicists try to apply quantum theory to the universe as a whole. In some models, the fundamental state of the universe is described by a wave function that does not depend on time. Instead of evolving, this wave function encodes all possible configurations of the universe in a single timeless object. To recover a sense of time, you look at correlations within this wave function. You pick one set of variables to act as a clock and see how other variables change in relation to it. For example, you might use the size of the universe or the value of a particular field as a reference. You then describe other features, like the distribution of matter, in terms of that reference. This is conceptually similar to using the pendulum to describe the light. The universe is not evolving in an external time. It is a collection of variables that can be related to each other in ways that look like evolution when viewed from the right perspective. This idea can feel abstract, but it has practical implications. It suggests that different choices of what you treat as a clock can lead to different descriptions of the same underlying reality. At large scales and in everyday situations, these different descriptions agree closely enough that we can talk about a single shared time. At very small scales or in extreme conditions, the differences might become more significant. There is also a link here to the way time appears in quantum mechanics. In standard quantum theory, the wave function evolves according to an equation that includes time as a parameter. But the theory does not provide an operator for time in the same way it provides operators for position or momentum. This asymmetry has puzzled physicists for a long time. It suggests that time plays a different role in the theory than other physical quantities. In a framework where time is emergent, this asymmetry might be less mysterious. Time is not a property of the system. It is a way of describing how the system changes relative to a chosen reference. This also sheds light on why measuring time is always about measuring change. A clock does not reveal time directly. It reveals the state of a system that changes in a regular way. You infer time from that change. Whether the clock is a swinging pendulum, a vibrating atom, or the rotation of the Earth, the principle is the same. You're comparing one process to another. This brings the discussion back to the idea of observers. An observer is not just a passive viewer of a pre-existing timeline. An observer is a system that uses some processes as references to organize the behavior of other processes. In this sense, time is partly a feature of how observers interact with the universe. It is a framework for organizing experience. not necessarily a fundamental ingredient of the world itself. This does not mean that time is purely subjective. Different observers can agree on time because they share physical processes that can be compared and synchronized. The fact that we can build clocks and coordinate them across the globe shows that there is a deep regularity in how systems change. What it means is that this regularity might itself be an emergent feature of a deeper, timeless structure. Another aspect worth considering is how this view of time interacts with causality. In everyday thinking, cause comes before effect. The past influences the present, which influences the future. In a timeless description, this ordering has to be reconstructed from correlations. You look at which systems carry records of which other systems. If System A contains information about System B in a way that System B does not contain information about System A, you infer that B is in the past of A. This idea has been explored in theoretical models where causality itself is treated as an emergent concept, derived from patterns of information flow rather than imposed as a fundamental rule. There is a quiet consistency to this picture. Space emerges from entanglement. Geometry emerges from quantum states. Gravity emerges from entropy. Time emerges from correlation and change. Each of the concepts that feel most basic to human experience becomes, in this view, a large-scale feature of a deeper, more abstract structure. This does not make those concepts less meaningful. On the contrary, it can make them more interesting. It suggests that the familiar world of clocks and calendars, of mornings and evenings, is a kind of interface, a way of interacting with a universe that is, at its deepest level, organized very differently. There is also a philosophical resonance here. Many traditions, long before modern physics, have questioned whether time is a fundamental aspect of reality or a feature of human perception. Physics, in its own precise and mathematical way, has arrived at a similar question, not through introspection, but through the attempt to make its most successful theories fit together. Still, it is important to remember that these ideas are not settled. There is no single, widely accepted theory that fully explains how time emerges from a timeless foundation. What exists instead is a collection of models, arguments, and hints that all suggest that the role of time in our deepest theories might be very different from the role it plays in everyday life. This uncertainty is not a weakness. It is a sign that physics is probing a boundary, a place where familiar concepts start to lose their clarity and new ones are needed. You can notice how the story has slowly moved from the structure of space to the structure of connection, from the flow of forces to the flow of information, and now from the ticking of clocks to the pattern of change itself. If space and time are emergent, if they arise from deeper relationships and correlations, then what does it mean to say that you are in a particular place at a particular moment? Picture a quiet moment where two people are standing in the same place, watching the same scene, yet describing it in slightly different ways. One notices the colour of the sky, the other notices the temperature of the air. Neither is wrong. Each is simply bringing a different frame of attention to the same situation. In physics, this simple idea is taken to a much deeper level, where the description of reality itself can depend on the perspective of the observer and the reference frame they occupy. The notion of a reference frame is, at its core, a way of saying where you are and how you are moving when you make a measurement. It is a set of assumptions about your state of motion, your orientation, and the tools you're using to define distances and times. Without some kind of reference frame, the words here, there, now, and then lose their meaning. Long before Einstein, physicists already understood that motion is relative. If you are sitting in a train that moves smoothly along a track, you can toss a ball straight up and watch it come back down into your hand. To you, the ball moves straight up and down. To someone standing on the platform as the train passes by, the same ball traces a curved path through the air. The two descriptions are different, but both are valid within their own frames of reference. Einstein took this idea and elevated it to a foundational principle. In special relativity, The laws of physics are the same in all inertial reference frames, meaning all frames that are moving at constant speed relative to each other. What changes from one frame to another are the measurements of space and time. Two observers moving relative to each other can disagree about how long a process took or how far apart two events were. They can even disagree about whether two events happened at the same time. There is no single, universal clock that everyone shares. This alone reshapes the way you think about reality. It suggests that space and time are not absolute backgrounds. They are part of the way different observers organize their experiences. General relativity extends this idea further. It says that reference frames are not just defined by motion, but also by gravity. An observer standing on the surface of the Earth experiences time differently from an observer far out in space, away from any massive objects. Clocks tick at different rates depending on the gravitational field they're in. This is not just a theoretical curiosity, it has practical consequences. The satellites that make up the GPS system experience both high speeds and weaker gravity compared to clocks on the ground. If these effects were not taken into account, GPS positions would drift by kilometers each day. In this way, the role of the observer is built into the fabric of modern physics. Measurements of space and time are not just about what is being measured, they're also about who is doing the measuring and how. Quantum theory brings a different kind of observer into the picture. Here, the issue is not just motion or gravity, it is the act of measurement itself. In quantum mechanics, the state of a system is described by a wave function that encodes a range of possible outcomes. When you perform a measurement, you do not simply reveal a pre-existing value. You force the system into one of those possible outcomes. This raises a subtle question. What exactly counts as an observer? Is it a conscious being? Is it a measuring device? Is it any physical system that can become correlated with the system being measured? Different interpretations of quantum theory answer this question in different ways. Some treat the wave function as a tool for calculating probabilities and view measurement as an update of information. Others treat the wave function as a real physical object and see measurement as a physical process that changes the state of the system. What they all agree on is that the act of observation cannot be cleanly separated from what is being observed. The observer is part of the story, not a detached spectator. When you combine this with the ideas you've been exploring about emergent spacetime, the role of the observer takes on a new dimension. If space and time themselves are not fundamental, but arise from deeper relationships, then the way an observer defines their reference frame might be part of how that emergence takes place. In other words, reality might not come with a built-in grid of coordinates. The grid might be something that observers, as physical systems within the universe, help to establish through their interactions and measurements. To see how this could work, consider again the idea of relational time. You do not measure time directly. You measure the change of one system relative to another. A clock is just a system that changes in a regular way. In the same spirit, you do not measure position directly. You measure the relationship between an object and something else, such as a ruler, a landmark, or another object. In this relational view, there is no absolute here or now. There are only relationships between systems. One system is here relative to another. One event is now relative to another. This does not mean that reality is purely subjective. Different observers can agree on relationships because they can interact and exchange information. They can compare their clocks, align their rulers, and synchronize their measurements. What it means is that the structure of space and time is built out of these shared relationships, not imposed from outside. There is an interesting parallel here with how coordinates work in mathematics. You can describe the same geometric shape using many different coordinate systems. You can use Cartesian coordinates, polar coordinates, or something more exotic. The shape itself does not depend on the coordinates you choose, but the way you describe it does. In physics, reference frames play a similar role. The underlying physical processes are the same, but the way you describe them depends on the frame you choose. When spacetime is treated as fundamental, this is mostly a matter of convenience. You pick a frame that makes the equations easier to work with. When spacetime is treated as emergent, the choice of frame might be more deeply connected to how the geometry itself is defined. This becomes especially interesting in quantum gravity, where the distinction between the system and the observer can become blurred. If the entire universe is a quantum system, then any observer is part of that system. There is no external vantage point. This raises the question of how to define an objective description of reality when every description is made from within. One way physicists approach this is by focusing on what different observers can agree on. Even if two observers describe a situation in different ways, there are quantities they can both measure and compare. These are often called invariants. In special relativity, for example, different observers can disagree about distances and times, but they agree on the spacetime interval between events. In quantum theory, different observers can describe a system using different bases, but they agree on probabilities for measurement outcomes. These shared features provide a kind of common ground. They are aspects of reality that do not depend on a particular frame of reference. In an emergent spacetime picture, these invariants might play an even more fundamental role. Instead of being derived from geometry, they might be the building blocks from which geometry is constructed. Another way to look at this is through the lens of information. An observer is a system that can store and process information. When an observer measures something, they create a correlation between their own state and the state of the system they are observing. This correlation is a physical process. It involves the exchange of energy, the alignment of states, and the creation of records. From this perspective, an observation is not just a mental act. It is a physical interaction that changes the structure of the universe, however slightly. If the geometry of space is tied to patterns of entanglement and information, then each observation, by changing those patterns, could be seen as contributing to the ongoing construction of space-time. This does not mean that observers are creating the universe in a dramatic, conscious way. It means that, as physical systems embedded in the universe, they participate in the network of interactions that give rise to its large-scale structure. There is also a connection here to the idea of coarse graining. An observer cannot access all the microscopic details of a system. They see only a limited, averaged picture. The geometry and physical laws they infer are descriptions of that average picture. Different observers, with different capabilities and limitations, might infer slightly different effective descriptions. At everyday scales, these differences are negligible. The world appears consistent and shared. At more extreme scales, or in more abstract models, the differences might become more pronounced. This leads to the idea that reality might have multiple, equally valid descriptions, each suited to a particular class of observers. This is already familiar in physics. A fluid can be described in terms of molecules or in terms of pressure and flow. Both descriptions are correct. They apply at different scales and to different kinds of questions. In the context of space-time and quantum theory, one description might be geometric and continuous. Another might be informational and discrete. The observer's role is to choose, often implicitly, which description is most useful for the situation at hand. There is also a subtle connection here to the concept of locality. In a geometric picture, locality is defined by distance. Systems that are close can interact. Systems that are far apart cannot, at least not directly. In an informational picture, locality might be defined by the strength of correlations. Systems that are strongly entangled are close in an informational sense, even if they are far apart in the emergent geometric sense. An observer's reference frame might determine which notion of closeness is most relevant. In everyday life, geometric closeness dominates. In quantum experiments, informational closeness can become more apparent. This dual notion of locality highlights how the observer's tools and perspective shape what they consider to be real and relevant. Another area where the role of the observer becomes important is in cosmology. When you look at the universe on the larger scales, you're not seeing it as it is now. You're seeing it as it was when the light you observe was emitted. This means that your picture of the cosmos is a kind of historical record. Different observers, located in different parts of the universe, will have different observable horizons. They will have access to different portions of the cosmic history. This is a large-scale version of the same principle that appears in black hole physics, where horizons limit what information is available to an observer. In all of these cases, the structure of what can be known is tied to the observer's position, motion, and capabilities. Reality, as experienced, is always filtered through a particular perspective. This does not mean that there is no underlying reality. It means that any description of it is necessarily partial. There is also a connection here to the idea of reference frames in more abstract spaces. In quantum theory, the state of a system can be described in many different bases. Choosing a basis is a bit like choosing a coordinate system. It determines how you label the components of the state. Different choices of basis can make different features of the system more or less apparent. One basis might highlight position, another might highlight momentum, another might highlight energy. None of these bases is the true one. They are different ways of organizing the same underlying information. This flexibility is a reminder that the language you use to describe a system is part of the description. It shapes what you see and what you consider to be a basic feature. When this idea is extended to spacetime itself, it suggests that the familiar grid of coordinates we use to map the world might be one of many possible ways of organizing the underlying quantum information. There is also a philosophical resonance here. In everyday life, you often find that two people can have very different perspectives on the same situation, and both can be valid. They notice different details, they care about different outcomes. Their experiences shape their interpretations. Physics, in its own formal way, seems to be telling a similar story about the universe. There is a structure that exists independently of any particular observer, but the way that structure appears depends on how and where you look. This becomes especially clear in situations where observers move at high speeds or experience strong gravity. Their measurements of time and space differ in precise, predictable ways. Quantum theory adds another layer, where the very act of looking changes what you see. In an emergent spacetime picture, these features are not just quirks of our measurement tools. They are clues about how the large-scale world is built from deeper relationships. The observer is not outside the system, looking in. The observer is part of the system, contributing to the web of interactions that gives rise to the system's structure. This idea can feel unsettling, because it challenges the image of a detached, objective viewpoint. But it can also feel quietly inclusive. It suggests that every act of observation, every measurement, every interaction is part of the universe's ongoing story. There is no single, final perspective from which everything can be seen at once. There are only many overlapping perspectives, each revealing a different aspect of the same underlying reality. Space emerges from connection. Time emerges from change. Gravity emerges from entropy. Geometry emerges from quantum states. And now, the way all of these things appear is shaped by the perspective of the observer. The picture that forms is not of a universe that simply exists as a fixed structure, waiting to be discovered, but of a universe that is, in some sense, continually being described and organized through the interactions of its own parts. This naturally leads to a question about what it means to live in such a world. If the universe is building itself moment by moment from relationships, correlations, and information, then what does it mean for something to have a place in that process? Imagine setting aside, just for a moment, every familiar marker you normally use to orient yourself. No up or down, no near or far, no before or after. What remains is not darkness or emptiness in the usual sense, but something more difficult to picture. A description of reality that does not rely on space as a container or time as a sequence. This is the kind of mental shift that comes into play when physicists talk about a universe that exists, at its deepest level, before space-time itself takes shape. The phrase pre-space-time can sound dramatic, as if it refers to a moment in the distant past, a time before the Big Bang. In many modern approaches, however, it does not mean earlier in a temporal sense, because time itself is part of what is being set aside. Instead, it refers to a layer of description that does not use space and time as fundamental ingredients at all. To understand why such an idea is even considered, it helps to recall the tension that runs through much of modern physics. On one side, you have general relativity, which describes gravity as the geometry of space-time. On the other side, you have quantum theory, which describes the world in terms of states, probabilities, and information. Each works extremely well in its own domain. When you try to combine them, the usual picture of a smooth, continuous space-time begins to strain and in some cases break down. At very small scales, near what is known as the Planck length, the fluctuations predicted by quantum theory become so strong that the idea of a well-defined geometry loses its clarity. Distances and durations stop being sharply defined. The notion of a point in space or an instant in time becomes fuzzy. This has led many researchers to suspect that space-time, as we know it, is not part of the most basic description of reality. Instead, it might be something that emerges when you look at a deeper structure from a certain perspective or at a certain scale. So what might that deeper structure be like? One way to approach this question is to think in terms of relationships rather than locations. Instead of imagining a set of points arranged in space, imagine a collection of elements that are connected in various ways. What matters is not where an element is, but how it is linked to others. This kind of picture shows up in several different theoretical frameworks. In some, the fundamental ingredients are abstract entities sometimes called nodes, events, or quantum systems. These elements are connected by links that represent interactions, correlations, or flows of information. The structure formed by these links can be thought of as a network or a graph. The network itself does not live in space. It does not have distances or directions in the usual sense. It simply has connections. From this network, something that looks like geometry can be reconstructed. If many elements are tightly connected to each other, they can be grouped into what appears, at a larger scale, to be a region of space. If two groups of elements are only weakly connected, they can appear far apart. In this way, distance becomes a measure of connectivity rather than a fundamental property. Another approach begins with quantum states. Instead of a network of nodes, you start with a large, complex quantum system described by a single global state. This state encodes all the possible ways the system can be configured and how its parts are correlated. Within this state, there are patterns of entanglement. Some parts of the system share a lot of information. Others share very little. By analysing these patterns, you can sometimes extract a notion of geometry. Regions of strong entanglement correspond to regions that look close together in an emergent space. Regions of weak entanglement correspond to areas that look far apart. In this view, a pre-space-time universe is not a place. It is a state. It is a mathematical object that contains information about how different degrees of freedom are related, but not about where they are in a geometric sense. There are also models that treat the fundamental structure as something like a causal network. In these, the basic elements are events, and the links between them represent which events can influence which others. This kind of structure does not require a pre-existing notion of time. It only requires a notion of ordering. One event can come before another if it can influence it. Another pair of events might be unrelated, neither influencing the other. From this partial ordering, something that looks like time can emerge. You can define a sequence of events along a chain of influence and treat that as a timeline. Different chains can give rise to different timelines, corresponding to different observers or reference systems. Similarly, by looking at how many events are linked to a given event and how those links are arranged, you can begin to reconstruct something that behaves like spatial geometry. These ideas suggest that a pre-space-time universe might be more like a set of rules for how things can be related than like a stage on which things happen. There is also an approach that starts from the idea of information as the most fundamental ingredient. In this view, the universe is, at its deepest level, a vast collection of informational degrees of freedom. These could be thought of as bits, or quantum bits, although they are not necessarily bits in the computer science sense. What matters is that there are states, and there are rules for how those states can change and influence each other. From these rules, patterns emerge. Some patterns are stable. They persist over many interactions. These stable patterns can be interpreted as particles, fields, or even regions of space. In this informational picture, a pre-spacetime universe is one where the only things that exist are informational relationships. Space and time are ways of organizing those relationships into a form that makes sense at large scales. There is a subtle but important distinction here. This does not mean that space and time are illusions. They are real at the level at which we experience them. What it means is that they might not be the most basic layer of description. A helpful analogy can be found in how you might think about a city. At one level, a city is a set of streets, buildings, and physical locations. At another level, it is a network of social relationships, economic exchanges, and flows of information. The physical map of the city is one way of representing it. The social network is another. Neither is the whole story. Each highlights different aspects of the same underlying system. In a pre-spacetime view of the universe, the geometric map is like the street map of the city. The deeper, more fundamental description is like the social network. This analogy can only go so far, but it captures the idea that what looks like a three-dimensional world might be one way of representing a more abstract structure. Another feature that often appears in these models is discreteness. Instead of a smooth, continuous space, the fundamental structure might be made up of discrete elements, like the pixels on a screen. At large scales, a screen looks smooth. You see images and colours. Up close, you see individual pixels. In a pre-spacetime universe, space might be like that. At everyday scales, it looks continuous. At the deepest level, it might be built from individual, discrete units of information or connection. This idea is attractive because it offers a way to avoid some of the infinities that appear when you try to describe a perfectly smooth space-time at arbitrarily small scales. However, it also raises new questions. What determines the size of these fundamental units? How do they combine to produce the smooth geometry we observe? What rules govern their interactions? These are active areas of research, and different theories propose different answers. Some approaches use mathematical structures known as spin networks or spin foams, where the fundamental elements are related to quantum properties of geometry itself. In these models, areas and volumes come in discrete chunks, rather than varying continuously. Others use ideas from computer science, treating the universe as something like a computational process, where the fundamental rules are about how bits of information are updated. Still others focus on algebraic structures, where the basic objects are not points or nodes, but abstract mathematical entities that encode relationships in a more general way. Despite their differences, these approaches share a common theme. They all move away from the idea that space and time are given from the start. They treat them as things to be explained, not things to be assumed. One of the challenges in thinking about a pre-spacetime universe is that our language is deeply tied to space and time. We talk about things being before or after, inside or outside, near or far. These words lose their usual meaning when the concepts they refer to are no longer fundamental. Physicists often have to rely on mathematical language to express these ideas precisely, because ordinary words can be misleading. Still, you can get a sense of what is being suggested by focusing on the idea of structure rather than location. The pre-spacetime universe is structured. It has rules. It has patterns. What it does not necessarily have is a geometric layout. There is also an interesting connection here to how you think about the origin of the universe. In the standard cosmological picture, you talk about the Big Bang as the beginning of space and time. In a pre-spacetime framework, the Big Bang might be better thought of as a transition, a change in the way the underlying structure is organized, from a phase where a geometric description does not make sense to a phase where it does. This is similar to how water can exist in different phases. At high temperatures, it is a gas. At lower temperatures, it is a liquid. The molecules are the same in both cases. What changes is the way they are arranged and how they move. In this analogy, spacetime is like the liquid phase. The pre-spacetime structure is like the gas phase. The transition between them is like a phase change. This perspective can help make sense of why the early universe appears so different from the universe we see today. The familiar rules of geometry and gravity might not have applied in the same way at very early stages. Another angle on this involves the idea of universality. In many physical systems, very different microscopic details can lead to the same large-scale behavior. For example, many different kinds of molecules can form a liquid that flows in similar ways. If space-time is an emergent phenomenon, it might be universal in this sense. Many different underlying structures could give rise to similar geometric behavior at large scales. This would mean that to some extent the details of the pre-spacetime universe might be hidden from us. What we can observe is the emergent geometry and the effective laws that govern it. This is both a limitation and an opportunity. It means that direct tests of pre-spacetime theories might be very difficult. It also means that the large-scale structure of the universe could provide clues about the deep underlying rules, even if those rules are not directly accessible. There is also a link here to the idea of renormalization, a technique used in physics to connect descriptions at different scales. Renormalization allows you to start with a detailed microscopic theory and derive an effective large-scale theory that ignores fine details. In the context of space-time, one can imagine a similar process, where you start with a pre-spacetime description and, by averaging over many degrees of freedom, arrive at a smooth geometric picture. This process of averaging and simplification could be what gives rise to the familiar laws of gravity and motion. Another aspect worth considering is how matter and energy fit into a pre-spacetime picture. In the usual view, matter exists in space and time. In a pre-spacetime view, matter might be another kind of emergent pattern. Particles could be stable, repeating structures in the underlying network or state. Fields could be collective modes of many underlying elements. This aligns with the idea that what we call stuff and what we call space might both be emergent from the same deeper substrate. In this sense, the distinction between matter and geometry becomes less sharp. Both are different ways of organizing the same underlying degrees of freedom. This can help explain why, in general relativity, matter tells spacetime how to curve, and spacetime tells matter how to move. They are not completely separate. They are two aspects of a single coupled system. In a pre-spacetime framework, that coupling might be a reflection of the fact that both matter and geometry arise from the same underlying structure. There is also a conceptual shift here in how you think about nothing. In everyday language, empty space is often thought of as nothing. In physics, even empty space is full of fields and fluctuations. In a pre-spacetime view, what lies beneath space might be even more active. It might be a dense web of information, connections, and potential interactions. The emergence of space and time from that web would then be a kind of simplification, a way of organizing a complex abstract structure into a form that can be navigated and described. This is a striking reversal of the usual intuition. Instead of thinking of space as a container that holds everything, you think of space as something that emerges from the relationships between things. As you sit with this idea, you might notice how it changes the feel of the word universe. It no longer refers just to a vast expanse of space filled with galaxies. It refers to a totality of relationships, states, and possibilities. The visible cosmos becomes one layer of a much deeper structure, like the surface of an ocean that hints at the currents and depths below. The final piece of this picture often returns to the role of observers. If space-time is emergent, then what observers experience as space and time depends on how they interact with the underlying structure. Different kinds of observers, with different capabilities and limitations, might carve out different effective geometries from the same pre-space-time substrate. At human scales, these differences wash out, and a shared, stable world appears. At more extreme scales, the differences might become more noticeable. This brings the exploration full circle. You started with the idea that space and time might not be fundamental. Along the way, you encountered entanglement, information, entropy, and emergence. Now, in the idea of a pre-space-time universe, all of these threads come together. The picture that forms is not of a universe that begins with the stage and then fills it with actors. It is of a universe that begins with relationships, rules, and patterns, and from those, gradually builds something that looks like a stage. From that stage arise distances, durations, forces, and histories. From those arise the familiar world of stars, planets, and living beings who can look out and wonder where they are and when they are. Step back for a moment from the details, the equations, and the careful language of theory, and consider the position you now find yourself in. After moving through ideas about entanglement, emergence, information, and the possibility of a reality beneath space and time, you're standing at a kind of conceptual edge. Not an edge in the sense of a physical boundary you could point to on a map, but an edge in understanding, where the questions begin to outnumber the answers, and where the tools of physics start to feel both powerful and incomplete at the same time. This is what it means, in a very practical sense, to be at the frontier of fundamental physics. It is not a single place or a single theory. It is a shifting region of inquiry where established ideas are stretched, tested, and sometimes set aside in favour of new ways of thinking. One of the defining features of this frontier is that it is shaped as much by what we do not know as by what we do. The history of physics is often told as a series of triumphs, moments when a new equation suddenly makes sense of a wide range of phenomena. Newton's laws, Maxwell's equations, Einstein's relativity, and the framework of quantum mechanics all fall into this category. But between these moments of clarity, there are long periods of uncertainty, where researchers explore many different paths without knowing which, if any, will lead to a lasting understanding. The current situation with space-time, gravity, and quantum theory fits squarely into this pattern. On one hand, general relativity and quantum mechanics are both extraordinarily successful within their own domains. On the other hand, they resist being combined into a single, coherent framework. This resistance is not a minor technical problem. It points to a deeper mismatch in how each theory describes the world. General relativity treats space-time as a smooth, continuous structure that can be curved and shaped by energy and matter. Quantum theory treats physical systems as collections of states and probabilities, where uncertainty and discreteness play a central role. When you try to apply quantum ideas to space-time itself, or geometric ideas to quantum states at the smallest scales, the usual concepts begin to blur. Distances become uncertain, times lose their sharpness. The idea of a well-defined point in space or moment in time becomes difficult to maintain. The frontier, then, is not just about finding the right mathematical formula. It is about finding the right way to talk about reality. One of the challenges at this edge is deciding which concepts are fundamental and which are emergent. Throughout this exploration, you've seen how space, time, geometry, gravity, and even the idea of a particle can be reinterpreted as large-scale features of a deeper, more abstract structure. This kind of shift is not unprecedented in science. Temperature, for example, feels like a basic property. You experience it directly as hot or cold. Yet at a deeper level, temperature is not a fundamental quantity. It emerges from the motion of many particles. Pressure is similar. It feels like a direct physical force, but it arises from countless tiny collisions between molecules and the walls of a container. If these familiar, everyday properties can be emergent, it becomes less surprising to consider that space and time might be emergent as well. What makes the current situation more challenging is that we do not yet have a clear picture of what they might be emerging from. Different approaches to fundamental physics propose different answers. Some focus on quantum information and entanglement. Some focus on networks of discrete elements. Some focus on algebraic structures or computational processes. Each of these approaches offers a different lens on the same underlying problem. Each highlights certain features and leaves others in the background. At the frontier, it is not always clear how these different approaches relate to each other. They might be pieces of a larger picture, or they might be competing paths, only one of which will lead to a lasting framework. This uncertainty is part of what makes the field both difficult and compelling. There is no single roadmap. Progress often comes from exploring unexpected connections between ideas that, at first glance, seem unrelated. One example of this is the way concepts from thermodynamics, a field originally developed to understand steam engines and heat flow, have become central to discussions about black holes, spacetime, and gravity. Another example is the role of information theory, which began as a way to understand communication and data transmission, and now plays a key role in how physicists think about quantum states, entanglement, and the structure of the universe. These crossovers suggest that the deepest description of reality might not belong entirely to any one traditional branch of physics. It might sit at the intersection of geometry, probability, computation, and information. Another feature of the frontier is the way it challenges intuition. Much of everyday reasoning is built around the idea that the world consists of objects in space, changing over time, influenced by forces. When you move into a framework where space and time themselves are not fundamental, this picture starts to unravel. You're asked to think in terms of relationships rather than locations, correlations rather than positions, and patterns of change rather than a flowing timeline. This can feel disorienting because the language you normally use to make sense of the world is tied so closely to spatial and temporal concepts. Even phrases like before and after, inside and outside, near and far, lose their usual meaning when those concepts are no longer taken as basic. Physicists often rely on mathematics to navigate this terrain, because mathematics allows you to express relationships without relying on spatial or temporal metaphors. A mathematical structure can encode connections, symmetries, and transformations in a way that does not require you to imagine a physical picture. Still, even with mathematics, interpretation remains a challenge. Two different mathematical frameworks can sometimes describe the same physical phenomena in very different ways. Deciding which description is more fundamental, or whether they are simply two perspectives on the same underlying reality, is not always straightforward. This brings up an important point about what it means to understand something in physics. Understanding is not just about having a set of equations that work, it is also about having a conceptual picture that helps you see how different pieces fit together. At the frontier, those conceptual pictures are often provisional. They are tools for thinking rather than final answers. They help guide research, suggest new questions, and point toward possible experiments or calculations. One of the persistent questions at this edge is how, if spacetime is emergent, the familiar laws of physics arise so reliably. Why does the world, at human and astronomical scales, obey simple, elegant equations that treat space and time as smooth and continuous? The answer, if emergence is the right path, likely has to do with universality. In many complex systems, very different microscopic details can lead to the same large-scale behaviour. For example, the flow of water can be described by the same equations whether the water is made of one type of molecule or another. If space-time and gravity are emergent, then the smooth, geometric behaviour described by general relativity might be a universal feature of a wide range of underlying structures. Many different microscopic realities could give rise to the same macroscopic geometry. This would explain why it is so hard to probe the deepest layer directly. The large-scale world might be insensitive to many of the details of the underlying structure, in the same way that the behaviour of a river does not depend on the exact shape of every individual water molecule. Another aspect of the frontier is the role of experiment and observation. The ideas you have been exploring about pre-spacetime structures and emergent geometry operate at scales that are far beyond the reach of current technology. The Planck scale, where these effects are expected to become most pronounced, is many orders of magnitude smaller than anything we can directly probe. This does not mean that the ideas are untestable. It means that tests are indirect. Physicists look for subtle signatures in cosmology, in the behaviour of black holes, in high-energy particle collisions, and in precision measurements of fundamental constants. They also use theoretical consistency as a guide. A proposed framework must reproduce the well-tested predictions of general relativity and quantum field theory in the regimes where those theories are known to work. It must not lead to contradictions or internal inconsistencies. This process can be slow and sometimes frustrating. It requires a balance between bold speculation and careful restraint. At the frontier, it is easy to be drawn to ideas that sound deep or elegant, but elegance alone is not enough. A theory has to be able to connect, at least in principle, to observation. This tension between imagination and evidence is a defining feature of fundamental physics. Without imagination, there is no progress. Without evidence, there is no anchor to reality. There is also a human side to this story that often goes unremarked. The frontier of physics is not just a set of abstract problems. It is a community of people, spread across the world, working in different traditions, with different intuitions and priorities. Some are drawn to mathematical beauty. Some are motivated by experimental challenges. Some are driven by philosophical questions about the nature of reality. These different motivations shape the kinds of questions that get asked, and the kinds of answers that are considered satisfying. This diversity can be a strength. It means that the same problem is approached from many angles, increasing the chance that a connection will be made that would otherwise be missed. At the same time, it can lead to debates and disagreements about what counts as progress. One group might see a new mathematical structure as a major breakthrough. Another might see it as interesting, but disconnected from physical reality. This kind of tension is part of the life of a field at the frontier. It reflects the fact that there is no clear, universally accepted path forward. Another feature of this edge is the way it blurs the line between physics and philosophy. Questions about whether space and time are fundamental, about the role of the observer, and about the nature of information have philosophical as well as scientific dimensions. In earlier periods of physics, such questions were often set aside as metaphysical. The focus was on calculating measurable quantities and making predictions. Today, as theories reach deeper into the structure of reality, these conceptual issues become harder to avoid. The way you interpret a mathematical framework can influence how you develop it and what kinds of extensions you consider. This does not mean that physics has become philosophy. It means that, at the deepest levels, the two are in conversation. Physics provides the formal tools and the connection to experiment. Philosophy provides a space to reflect on what the formalism might mean. Another question that often arises at this frontier is whether there is a final, ultimate description of reality waiting to be discovered, or whether the process of refinement and reinterpretation will continue indefinitely. Some physicists hope for a single, coherent framework that unifies all forces and all phenomena. Others suspect that any such framework will itself be an effective description, valid within a certain domain, but not the final word. The history of science offers examples in both directions. Newton's laws were once seen as the ultimate description of motion. They were later understood as an approximation within a broader framework. Quantum mechanics and relativity, in turn, might one day be seen as parts of an even larger picture. From this perspective, the idea of a final theory becomes less about reaching an endpoint and more about finding deeper and more unifying ways of describing the world. There is also a quiet, personal dimension to standing at this kind of frontier. When you think about the possibility that space and time, the most basic features of experience might be emergent, it can change how you think about your own place in the universe. You're no longer just an object moving through a pre-existing stage. You're part of a network of interactions, correlations, and information flows that, at large scales, take on the form of a world with places and moments. This does not make your experience less real. It situates it within a larger, more intricate structure. The feeling of being here now becomes one layer of a much deeper story. A story about how complex patterns arise from simpler rules, and how those patterns, in turn, give rise to the experiences and questions that lead you to explore those rules in the first place. There is a kind of symmetry in that. The universe, through the medium of human curiosity, becomes aware of its own structure, at least in a limited way. As this exploration comes to a gentle pause, it is worth noticing that nothing has truly been concluded. There is no final answer to take away, no single equation that neatly wraps everything up. What there is instead is a landscape of ideas, connections, and open questions, a sense that the world might be deeper, more relational, and more subtle than the familiar picture of objects in space and time suggests. The frontier of fundamental physics is not a wall, it is a horizon. As you approach it, new questions come into view, and the ones behind you take on a different shape. The ideas you've encountered about entanglement, information, emergence, and the possibility of a reality beneath space-time are not endpoints. They are signposts, markers of where current understanding has reached and where it might go next. From here, the path does not lead in a single straight line. It branches into many directions, some mathematical, some experimental, some conceptual, and in that branching, there is a quiet continuity. The same curiosity that led people to wonder about the motion of the stars and the fall of an apple now leads them to wonder about the structure of reality itself. The scale of the questions has changed. The spirit of inquiry has not. So rather than closing with a conclusion, it feels more fitting to leave this as an open space, a moment of stillness at the edge of what is currently known, a place where the familiar ideas of space, time, and matter fade into a more abstract landscape of relationships, patterns, and possibilities. And in that open space there remains the simple, persistent act of wondering, not as a step toward a final answer, but as a way of continuing the conversation between the universe and the minds that have grown within it.